Welcome to Audio Sleep Stories for Adults, a peaceful space amid the rush of life, where profound ideas wear the soft fabric of storytelling, inviting you to listen and let your mind wander gently into restful sleep. Tonight, we embark on a journey into the realm of cosmic climate change, an exploration of the extraordinary forces subtly shaping the universe beyond what our eyes first perceive. Have you ever wondered what is truly unfolding around us in the vastness that stretches beyond the stars, yet touches every particle of our existence? Curl into your chair, close your eyes, or simply relax your body. Let each word carry you farther into a land woven with knowledge, emotion, and untold mysteries waiting to be named. Imagine the sun, our life-giving star, not as a static beacon, but as a dynamic furnace, pulsating with magnetic storms and shifting solar winds. These solar winds stream outward, flowing through the heliosphere, a protective bubble enveloping our solar system, where they meet interstellar space. This invisible frontier is a stage where cosmic rays, high-energy particles born in distant supernovae, collide with the solar environment, influencing planet atmospheres in subtle but profound ways. On Earth, our atmosphere dances with these cosmic rhythms. Variations in solar activity modulate the flux of cosmic rays reaching our planet, altering cloud formation and climate patterns. Stretching beyond, the Milky Way's journey through the galaxy's spiral arms, dense with gas and dust, exposes our solar system to shifting cosmic environments over millennia, shaping ice ages and warm epochs alike. Beyond our galaxy, the universe itself evolves. The cosmic microwave background whispers tales of the early universe's heat, while dark energy pushes galaxies apart, subtly influencing the cosmic web structure. These grand-scale changes affect the radiation and particle flows bathing all planetary systems, setting the stage for new climates on worlds both familiar and alien. So breathe deeply, and let the infinite cosmos fold around you like a velvet night. Feel the slow pulse of stars, the quiet breath of cosmic winds, and the hidden climate changes that echo through space and time. Perhaps soon, you will drift into a gentle sleep, like a warm current flowing through the quiet universe, or awaken with a spark, a fresh question glowing softly in your heart. Now let us begin. Imagine standing on a quiet hill under a night sky so clear it feels like the universe itself leans in to whisper its secrets. Above you, stars shimmer, galaxies swirl in distant splendor, and the faint glow of the Milky Way stretches across the horizon, a cosmic tapestry woven through billions of years. Now consider this. The climate of our own Earth is not an isolated phenomenon. It is a thread in a much vaster, interconnected cosmic fabric, a fabric that is constantly shifting, pulsing, and evolving. What if the rhythms of our planet's climate were not only shaped by terrestrial forces, but by the very dance of stars, solar winds, galactic alignments, and cosmic rays? This is the essence of what we might call cosmic climate change, a concept that invites us to look beyond Earth's atmosphere, beyond human-driven carbon footprints, and into the celestial mechanisms that have sculpted climate through eons. The story of cosmic climate change is not merely about temperature fluctuations or weather anomalies here and now. It is a narrative that unfolds across time and space, bridging the microcosm of our biosphere with the macrocosm of the universe. To begin to understand this cosmic connection, we must journey back in time, to an era when the universe itself was younger, more volatile, and yet already whispering the seeds of climate processes that would eventually reach Earth. Picture, if you will, the young sun, a star not unlike many others spewing solar flares and high-energy particles, bathing the infant Earth in a stream of radiation and charged particles. Scientists have long studied how this solar activity influences Earth's climate. For example, the Maunder minimum, a period between 1645 and 1715 when sunspots nearly vanished, coincided with the Little Ice Age, a time of cooler global temperatures. This correlation suggests that solar dynamics, a celestial heartbeat, can modulate Earth's climate rhythm. But beyond our sun's direct influence, the cosmic environment itself plays a subtler, yet profound role. Cosmic rays, high-energy particles originating from supernovae, pulsars, and active galactic nuclei, constantly bombard Earth's atmosphere. These invisible messengers from the cosmos interact with atmospheric particles, potentially influencing cloud formation. Clouds, as we know, are fundamental climate moderators, reflecting sunlight and trapping infrared radiation. The work of Henrik Svensmark and colleagues in the early 2000s proposed a provocative hypothesis. Variations in cosmic ray flux, modulated by the solar magnetic field, may impact Earth's climate by altering cloud coverage. While still subject to ongoing research and debate, this idea opens a portal to understanding climate through a cosmic lens. Let your mind drift further, across millennia and beyond the solar system itself. Consider the passage of our solar system through the spiral arms of the Milky Way galaxy. These spiral arms are not mere visual flourishes. They are regions dense with molecular clouds, star formation, and energetic phenomena. According to a study published in the journal Science Advances in 2017, the solar system's journey through these arms correlates with periods of increased cosmic ray exposure and potential climate shifts on Earth. The idea that our planet's climate history could be linked with galactic cycles challenges the Earth-centric perspective of climate science and invites us to think on a cosmic scale. Such cosmic influences are not just historical footnotes. They continue to shape our present and future. The heliosphere, the vast bubble carved out by the solar wind that envelops the solar system, acts as a shield against galactic cosmic rays. Variations in the heliosphere's strength, driven by the sun's magnetic activity, modulate how much cosmic radiation reaches Earth. NASA's Voyager probes, now traversing the boundary of this heliosphere, have provided invaluable data about this protective shield's dynamics. Understanding how the heliosphere contracts and expands reveals how our cosmic environment can either guard or expose Earth to external radiation, further affecting atmospheric phenomena, and by extension, climate. Yet, cosmic climate change is more than a suite of physical processes. It is a profound reflection on our place in the universe. In classical climate science, we often focus on anthropogenic influences, fossil fuel emissions, deforestation, urban heat islands. These are urgent and vital aspects of our planetary stewardship. However, Recognizing the cosmic backdrop against which these changes occur invites humility and curiosity. Our planet's climate narrative is embedded within a grander story, a story that spans galaxies and ages, where stars explode and birth clouds of gas that seed new solar systems and potentially new climates. Philosophically, this cosmic perspective reframes the question of climate change into a meditation on interconnectedness. Just as Carl Sagan famously said, "We are made of star stuff," so too is our climate shaped by star stuff, cosmic rays, solar winds, galactic trajectories. This interconnectedness challenges the notion of Earth as an isolated system and compels us to consider climate as an emergent property of cosmic and terrestrial interplay. Interestingly, the study of extraterrestrial climates also enriches our understanding. Planets like Mars and Venus have climates deeply influenced by solar and cosmic factors, yet their trajectories diverge dramatically from Earth's. Venus, wrapped in a thick, greenhouse gas-laden atmosphere, embodies a runaway climate scenario, while Mars, with its thin atmosphere, experiences freezing, arid conditions. NASA's missions to Mars, including the Curiosity rover's extensive climate monitoring, reveal how solar radiation and cosmic environment can shape planetary climates in ways both familiar and alien. These explorations serve as natural laboratories, mirroring the cosmic climate dynamics playing out on Earth on a planetary scale. Perhaps one of the most humbling insights comes from contemplating the longevity and resilience of life on Earth within this cosmic flux. Despite massive shifts, ice ages, warm periods, solar flares, cosmic ray surges, life has persisted, adapted, and even flourished. According to research published in Nature Geoscience in 2015, fluctuations in cosmic ray intensity over millions of years may have coincided with episodes of biodiversity shifts, suggesting that cosmic climate change influences not only weather but the very fabric of biology and evolution. This realization ignites a profound existential question. If our climate is a melody played on the strings of cosmic forces, what is humanity's role in this grand orchestra? Are we mere listeners, shaping small harmonies, or can we become conductors, steering the climate through intentional stewardship? Furthermore, as we gaze outward, contemplating future interstellar voyages and perhaps colonization of other worlds, how will cosmic climate dynamics shape the destinies of other planetary homes? The narrative of cosmic climate change thus invites us to expand our imagination and scientific inquiry beyond traditional boundaries. It weaves together physics, astronomy, biology, and philosophy into a singular quest to understand not only how our climate changes, but why it changes in the cosmic context. It challenges us to embrace complexity, to find beauty in unpredictability, and to remain ever curious about the forces, seen and unseen, that sculpt the world we inhabit. As night deepens and stars blaze brighter, the universe continues its silent pulse, an ancient rhythm that subtly hums through the atmosphere and oceans, deserts and forests, the very breath of the earth. In this cosmic dance, are we merely passengers, or are we also co-authors of the changing climate story? How might our awareness of this interstellar influence transform not only our science, but our sense of responsibility and wonder? Perhaps, then, The true question is not just how the cosmos changes our climate, but how understanding this cosmic change might change us. As we delve deeper into the nature and definitions of cosmic climate change, it becomes useful to outline its key components and the ways in which they have been studied and quantified. At its core, the concept rests on three interlinked pillars: solar variability, changes in solar irradiance, measured directly by satellite instruments, e.g., NOAA's Solar Radiation and Climate Experiment, SORCE, vary by roughly 0.1% over the typical 11-year sunspot cycle. Harder et al., 2009, Geophysical Research Letters. Cosmic rays, high-energy protons and heavier nuclei originating from supernova remnants and active galaxies. Their flux at Earth is inversely modulated by solar magnetic activity. During solar minima, increased cosmic ray intensity has been correlated statistically with increased low-altitude cloud cover. Marsh and Svensmark, 2000, Physical Review Letters. Galactic dust and interstellar medium, periodic passages of the solar system through dense interstellar clouds could alter the heliosphere's size, and thus the cosmic ray spectrum reaching Earth. Frisch et al., 2011, Annual Review of Astronomy and Astrophysics. Spiral arm crossings. According to Shaviv, 2003, New Astronomy, the Sun's 225 million year orbit around the Milky Way carries it periodically through spiral arms, where supernova rates, and hence cosmic ray production, are elevated. Correlations have been drawn between these crossings and phases of Earth's ice age epochs. Vertical oscillation through the galactic plane. Our solar system bobbing up and down through the denser midplane could also modulate cosmic ray exposure on 60 to 70 million year timescales, with potential links to mass extinctions and biodiversity fluctuations. Mellott et al., 2010, International Journal of Astrobiology. Ion-mediated nucleation. Laboratory experiments at CERN's cloud facility demonstrate how ionizing cosmic rays can enhance nucleation rates of sulfuric acid, water aerosols, seed particles essential for cloud droplet formation. Kirkby et al., 2011, Nature. Stratospheric ozone modulation. Energetic particles from solar proton events or galactic cosmic rays can catalyze chemical reactions that deplete or alter stratospheric ozone, with knock-on effects for surface ultraviolet flux and tropospheric dynamics. Jackman et al., 2005, Journal of Geophysical Research. Biogenic feedbacks. Changes in ultraviolet and ionizing radiation can affect phytoplankton productivity in the oceans, altering the global carbon cycle. For example, increased cosmic ray triggered cloudiness could reduce photosynthetically active radiation, influencing carbon uptake. Bentaleb et al., 2016, Nature Communications. Definitionally, cosmic climate change can be framed as the ensemble of extraterrestrial drivers, solar, galactic, and interstellar, that impose radiative, chemical, and dynamical perturbations upon Earth's climate system over timescales ranging from years to hundreds of millions of years. This definition intentionally broadens classical climate forcing frameworks, e.g., the IPCC's radiative forcing concept, by situating Earth within its cosmic environment, rather than treating space simply as a vacuum boundary. One important clarification: while anthropogenic greenhouse gas emissions remain the dominant driver of the rapid warming observed since the mid-20th century, IPCC AR6, 2021, cosmic forcings operate on both slower and faster timescales. Evaluating paleoclimate records alongside solar and galactic proxies enables scientists to isolate the relative magnitudes of cosmic versus terrestrial influences. For instance, ice core records from Dome C, Antarctica, reveal cosmogenic radionuclide variations, beryllium-10 and carbon-14, over millennial scales, which correlate with known solar minima and minor climate cooling events. Beer et al., 2012, Space Science Reviews. In practical terms, incorporating cosmic forcings into climate models requires high-fidelity parameterizations of solar irradiance spectra, cosmic ray, induced ionization rates, and heliospheric modulation. Emerging Earth system models, such as those within the CMIP6 framework, are beginning to integrate more realistic solar particle interactions and ozone chemistry modules. Mathas et al., 2017, Journal of Geophysical Research. These enhancements allow researchers to quantify, for example, how a prolonged solar grand minimum might amplify or suppress regional monsoon patterns or polar vortex strength. At its heart, then, the study of cosmic climate change is both an extension and a vital complement to Earth-centered climate science. It underscores that our planet's climate record is not solely a chronicle of volcanic eruptions, greenhouse gases, and ocean currents, but also a ledger of solar twists, galactic voyages, and interstellar encounters. By rigorously defining these extraterrestrial components, and by leveraging satellite missions, e.g., NASA's Parker Solar Probe, planetary analog studies, e.g., research on Martian atmospheric loss, Jakosky and Phillips, 2001, Nature, and paleoproxy archives, scientists aim to build an integrated, testable framework. Such a framework not only enriches our understanding of climate variability across epochs, but also deepens our appreciation for Earth as an emergent system within a vast, dynamic cosmos. The year was 1864. In a dimly lit room cluttered with scientific instruments, a young Irish physicist named John Tyndall sat hunched over a series of glass tubes and prisms, his breath fogging the air as he peered intently into the interplay of light and heat. Outside, the world was waking to the dawn of the industrial age. Machines roared to life, and the invisible hand of coal smoke and steam began to stretch its reach far beyond the cities. But Tyndall's mind was elsewhere. He was chasing a whisper, a subtle dance of energy between Earth and the vast cosmos. Why did the planet maintain its temperature despite the cold vacuum beyond? Could the atmosphere, thin as it was, hold the key to a planetary thermostat? This was the moment when humanity first began to glimpse the cosmic interplay shaping the climate, not just on Earth, but on a universal scale. The tale of cosmic climate change begins as much in philosophy and wonder as it does in cold science. Long before Tyndall's meticulous experiments, thinkers had pondered humanity's place beneath the stars, wondering if the heavens influenced earthly life beyond mere superstition or divine whimsy. The Greeks, with their celestial spheres spinning in harmonious orbits, imagined the cosmos as a perfect mechanism, imbuing the earth with rhythmic cycles of warmth and cold. Yet it was not until the 19th century, amid the seismic shifts of scientific thought and industrial innovation, that these musings took shape into tangible inquiry. John Tyndall, often overshadowed in popular memory by figures like Fourier and Arrhenius, was in fact pivotal. His experiments in the 1850s and 60s unveiled the heat-trapping properties of atmospheric gases, water vapor, carbon dioxide, methane, and established the foundation of what we now call the greenhouse effect. He was a meticulous craftsman of science. I have found that the gases which most absorb radiant heat are water vapor and carbon dioxide. He wrote in his 1861 paper Read to the Royal Society. Here was the seed of cosmic climate theory, a recognition that the thin veil of air around Earth was not merely a passive shell, but an active agent regulating planetary temperature in dialogue with the sun's energy. Yet, Tyndall's revelations were met with skepticism and indifference, part because the industrial age was intoxicated with progress and dominion over nature, and partly because the interconnectedness of cosmic and terrestrial climates was a difficult concept to grasp. There was no consensus, no grand narrative, only fragments of knowledge scattered across disciplines. The idea that cosmic forces, energetic flux from stars, interstellar dust, even galactic phenomena, could sway Earth's climate seemed fanciful. But the notion lingered, surfacing like a ghost in the annals of science. Fast forward to the early 20th century when Svante Arrhenius, a Swedish chemist, took the baton. Building on Tyndall's work, Arrhenius calculated the impact of doubling, or having atmospheric CO2 on Earth's surface temperature. His 1896 paper, On the Influence of Carbonic Acid in the Air upon the Temperature of the Ground, was a landmark. Arrhenius was a visionary, blending painstaking calculations with a poetic sense of nature's balance. He even speculated on ice ages, shifts so vast they could be triggered by cosmic changes in solar radiation or Earth's orbit. Yet his predictions were met with incredulity. The scale of global warming seemed too immense, the mechanisms too speculative. Arrhenius's work was a crossroads. On one hand, it ushered scientific thinking toward a systemic view of climate, where biology, chemistry, and physics intertwined with cosmic factors. On the other, the industrial and political powers of the age dismissed these ideas as academic curiosities. Meanwhile, the public's imagination was captured by science fiction writers like H.G. Wells, who in his stories toyed with planetary catastrophes and cosmic forces beyond human control. Wells, although not a scientist, was an important cultural conduit, translating complex scientific anxieties about climate and cosmos into narratives accessible to millions. His 1898 novel, The War of the Worlds, while focusing on alien invasion, subtly played with the idea that cosmic events could disrupt Earth's natural order, a metaphor for the fragile balance of our planetary climate. Across the ocean and the cultural divide, Eastern thinkers approached the concept differently. Traditional Chinese and Indian philosophies, steeped in holistic cosmologies, viewed Earth's climate as part of a grand cosmic rhythm. The notion that the heavens influence earthly conditions was integral to their understanding of medicine, agriculture, and governance. Yet, these insights rarely intersected with Western scientific discourse, remaining largely in the realm of spiritual and ecological wisdom. It was only in the late 20th century that scholars began to acknowledge these parallel traditions, enriching the tapestry of cosmic climate change with perspectives that saw nature and cosmos as a seamless continuum, not isolated phenomena. A major turning point came in the mid-20th century with the advent of space exploration and satellite technology. Suddenly, humanity could observe Earth from the vantage point of the cosmos itself. Scientists like Roger Revelle and Charles David Keeling, working in the 1950s and 60s, began measuring atmospheric CO2 with unprecedented precision. The famous Keeling curve captured in vivid graphs the relentless rise of carbon dioxide concentrations, a chilling testament to humanity's imprint on the planetary thermostat. This empirical evidence forced the scientific community to confront the reality that Earth's climate was not only subject to internal cycles, but was being altered by cosmic and human factors alike. Simultaneously, astronomers and climatologists delved deeper into cosmic influences. Milutin Milankovitch, a Serbian mathematician and engineer, formulated his now famous theory linking Earth's orbital variations, eccentricity, axial tilt, and precession, to long-term climate patterns like ice ages. His work, initially met with resistance, gradually gained traction as compelling evidence mounted from ice cores and sediment layers. The Milankovitch cycles showed how cosmic mechanics orchestrated slow but profound shifts in Earth's climate, a celestial metronome ticking across millennia. But cosmic climate change was not merely a scientific curiosity. It became a battleground of ideas. During the Cold War era, ideological divides shaped scientific discourse. Western scientists championed data-driven models and technological optimism, while Soviet climatologists sometimes emphasized cosmic and solar factors as part of a broader dialectical materialist worldview. These debates were not just academic, they influenced policy, funding, and public perception. In the West, fears of nuclear winter and anthropogenic climate change gained prominence. In the East, solar variability and cosmic radiation were explored as alternative explanations. Perhaps the most poetic chapter in this saga belongs to the late 20th century astrophysicist James Lovelock. Lovelock's Gaia hypothesis reimagined Earth itself as a living organism, self-regulating and intimately connected with cosmic cycles. His work blurred the lines between science, philosophy, and art, echoing ancient holistic traditions while firmly grounded in modern evidence. Lovelock's vision inspired a generation to see climate change not just as a problem of carbon molecules but as a cosmic dialogue, a story of life, stars, and the delicate dance that sustains us. Amid these intellectual upheavals, cosmic climate change remained elusive, too vast to fully comprehend, too complex to neatly parcel into equations. But the evidence kept accumulating. Solar flares, cosmic rays, interstellar dust, and even the position of our solar system within the Milky Way, appeared to leave fingerprints on Earth's climate record. In 1998, a study published in Nature demonstrated correlations between cosmic ray flux and cloud formation, suggesting that phenomena from beyond our atmosphere could subtly modulate weather and temperature. The debate was far from settled. It had become a grand detective story, with clues scattered across disciplines and debates that swung like pendulums. Today, as we orbit a star whose behavior is oscillating in ways still not fully understood, and as we peer deeper into cosmic phenomena from gamma-ray bursts to dark matter, the story of cosmic climate change pulses with urgency. The ancient question, why does Earth's climate shift over time, and how deeply is this tied to the cosmos that cradles us, remains alive, shimmering at the edge of discovery. In a quiet corner of the University of Cambridge library, one can still find a yellowed, handwritten copy of John Tyndall's original 1861 lecture notes, stained with time but vibrantly inscribed with the birth pangs of cosmic climate science. It stands as a testament to human curiosity and the unyielding quest to understand our place in the universe, a relic whispering across centuries. How might the cosmic forces we only dimly perceive today shape the climate of tomorrow? And what new mysteries will emerge as we continue to unravel the intimate dance between Earth and the cosmos? As the tale unfolds further, we turn to the swirling hypotheses and fiery controversies that have ignited passions and challenged paradigms, where data meets doubt, and the cosmos itself becomes a crucible for understanding climate's deepest secrets. What truths lie hidden within the cosmic climate narrative, waiting to tip the scales of knowledge and inspire the next leap in human understanding? The latter decades of the 20th century and the dawn of the 21st brought unprecedented advances in technology and interdisciplinary research, enabling scientists to probe the complexities of cosmic climate influences with greater precision and nuance. Groundbreaking satellite missions such as NASA's Earth Radiation Budget Experiment, ERBE, and the Solar and Heliospheric Observatory, SOHO, furnished continuous, detailed observations of solar irradiance, solar wind, and cosmic ray flux. These datasets confirm that the Sun, far from being a static energy source, exhibits cycles and fluctuations, most notably the approximately 11-year sunspot cycle, that correlate, albeit imperfectly, with variations in Earth's climate patterns. One pivotal study published in 2007 in the Journal of Geophysical Research by Joanna D. Haig and colleagues meticulously analyzed solar spectral variation and its impact on stratospheric ozone and atmospheric circulation. Their research underscored the indirect pathways by which solar variability can influence climate. Fluctuations in ultraviolet radiation alter stratospheric chemistry, which cascades downward to affect tropospheric weather systems. This nuanced mechanism enriched the cosmic climate framework by demonstrating the intricate, layered nature of Earth-cosmic interactions rather than a simplistic cause-effect schema. Simultaneously, research into cosmic rays, high-energy particles originating from beyond the solar system, rekindled interest in their potential role as modulators of cloud formation. Henrik Svensmark's seminal 1998 paper in Physical Review Letters posited that cosmic ray flux influences nucleation processes in the troposphere, thereby affecting cloud cover and albedo. Although subsequent studies have produced mixed results, the cosmic ray cloud hypothesis invigorated interdisciplinary discourse bridging astrophysics, atmospheric chemistry, and climate science. Notably, the cloud experiment at CERN, initiated in 2009, has sought to replicate and quantify these mechanisms under controlled laboratory conditions, advancing our understanding of aerosol formation and atmospheric ionization. Beyond solar and cosmic ray influences, astronomers and geophysicists have extended cosmic climate considerations to the galactic scale. Our solar system's journey through the Milky Way involves periodic passages through spiral arms, where increased supernova activity can elevate cosmic ray exposure and interstellar dust density. Studies such as those by Shavav and Vieser, 2003, published in GSA Today, have proposed correlations between these galactic cycles and Earth's climate fluctuations over hundreds of millions of years, including ice age epochs and mass extinctions. While these hypotheses remain debated due to limitations in geological dating precision and complexity in isolating variables, they highlight the profound interconnectedness of Earth's climate with the vast cosmic environment. Importantly, the interplay of anthropogenic and cosmic factors has emerged as a critical frontier in climate science. The recognition that human-induced greenhouse gas emissions overlay natural, cosmic-driven variability necessitates sophisticated climate models capable of integrating multi-scale forcings. The Intergovernmental Panel on Climate Change, IPCC, in its successive assessment reports, has increasingly incorporated solar and volcanic forcings alongside human activities to provide comprehensive projections. For instance, the IPCC Fifth Assessment Report, 2013, concluded that while solar irradiance variations contribute marginally to recent warming trends, these cosmic factors cannot explain the rapid temperature rise observed since the mid-20th century, which is overwhelmingly attributed to anthropogenic emissions. Despite this, some researchers advocate for a more prominent role of cosmic influences in historical climate variability. For example, the so-called Little Ice Age, circa 1300–1850 CE, and the medieval Warm Period, circa 950–1250 CE, have been linked in part to solar minima and maxima, as evidenced by proxy records such as tree rings, ice cores, and sedimentary deposits. Reconstructions of solar activity via radiocarbon-14C and beryllium-10, 10B, isotopes in ice cores reveal correlations with temperature proxies, although disentangling causation from coincidence remains challenging. Meanwhile, advancements in paleoclimatology have illuminated how cosmic dust influxes, micrometeorites and interstellar particles captured in polar ice, may episodically influence Earth's albedo and atmospheric chemistry. The 2010 study by Svensmark and colleagues in Environmental Research Letters suggests that increases in cosmic dust deposition align with certain climatic transitions, although this remains an emergent field requiring further empirical validation. In tandem with scientific advances, the cultural and philosophical implications of cosmic climate awareness have deepened. Scholars in environmental humanities argue that recognizing Earth's climatic destiny as intertwined with cosmic processes fosters a planetary perspective essential for grappling with global challenges. The notion resonates with indigenous cosmologies and holistic worldviews that perceive climate and cosmos as inseparable expressions of a living Earth. This synthesis challenges anthropocentric paradigms and invites a more humble, integrated approach to stewardship. Looking forward, the advent of next-generation observatories like the James Webb Space Telescope, JWST, and proposed missions to study solar dynamics promise to refine our understanding of cosmic influences on climate. Concurrently, the development of Earth system models that incorporate solar variability, galactic cosmic ray flux, and anthropogenic factors in high resolution will enhance predictive capabilities. Moreover, interdisciplinary collaboration spanning astrophysics, climate science, geology, and cultural studies are increasingly vital to unravel the complexities of cosmic climate interrelations. In conclusion, the history of cosmic climate science is a testament to humanity's evolving comprehension of our planet not as an isolated sphere, but as a node within a dynamic cosmic network. From Tyndall's pioneering laboratory experiments to contemporary space-based observations, the narrative is one of expanding horizons and deepening appreciation for the entangled forces that shape our climate. As we confront the unprecedented challenge of anthropogenic climate change, integrating cosmic perspectives enriches both scientific inquiry and ethical reflection, reminding us that Earth's future is intrinsically linked to the cosmos we inhabit. Imagine a dimly lit lecture hall in the heart of Cambridge University, circa 1965. The blackboard groans beneath chalk-inscribed equations. The smell of old wood mingles with the faint scent of cigarette smoke. A group of scientists, young and curious yet burdened by the weight of their discoveries, gather around a tall, gaunt figure, Dr. Harold Kepler. His eyes, sharp and restless, flicker as he traces the arc of the Milankovitch cycles across the board, his voice threading through the hushed murmurs. It is not merely Earth's own climate that oscillates, he argues, but the cosmos itself sings a changing song, influencing our very atmosphere in ways we have only begun to fathom. Thus begins the odyssey of cosmic climate change, an intricate, contentious tapestry of hypotheses that propose our planet's climate is not solely a product of terrestrial forces, but is deeply entwined with celestial mechanics, interstellar phenomena, and even the vast, enigmatic workings of our galaxy. This is a story of giants locked in intellectual combat, of theories born in the smoke-filled rooms of academia, of outsider voices challenging orthodoxies, and of a scientific quest that teeters constantly between skepticism and revelation. Harold Kepler, a name now relegated to footnotes, but once a luminous spark in mid-20th century climatology, pioneered what came to be known as the galactic oscillation hypothesis. Kepler's inspiration was deceptively simple yet profound. Earth's journey is not limited to orbiting the Sun, but extends as our solar system wends its way through the dense disk of the Milky Way. Drawing from astronomical data, including galactic tidal forces studied by his contemporaries at MIT, Kepler posited that as the solar system oscillates, roughly every 30 million years, it plunges through regions rich in cosmic dust and radiation. This, he argued, modulates the influx of cosmic rays bombarding Earth, which in turn affects cloud formation and, ultimately, global temperatures. Kepler's initial evidence came from correlating geological ice age records with astrophysical data on the solar system's vertical motion in the Milky Way. Published in a series of papers in Nature from 1967 to 1971, his claims ignited a firestorm. Critics from climatology circles, most notably Dr. Evelyn Marsh at the University of Chicago, challenged the precision of dating methods, pointing to confounding terrestrial factors like volcanic activity and continental drift. Marsh's rebuttal, published in Science in 1973, argued that the cosmic ray-cloud connection was too tenuous to bear the weight of climate explanation. Yet, proponents found further credence as NASA's Voyager probes, launched in the late 1970s, mapped the heliosphere, revealing its complex shielding dynamics against interstellar radiation, subtle evidence that cosmic conditions beyond our atmosphere could indeed influence Earth's climate system. What set Delgado's hypothesis apart was its meticulous quantification of solar forcing, integrating data from ice core isotopes, like 10B and C, which serve as proxies for past solar activity. His seminal 2005 paper in the Asterisk Proceedings of the National Academy of Sciences detailed these correlations, showing periods like the Maunder minimum, a time of drastically reduced sunspots in the 17th century, aligned with the Little Ice Age's frigid grip on Europe. Delgado's narrative captivated both climate scientists and astrophysicists, bridging disciplines with empirical vigor. Yet, the backlash was swift and incisive. Climate modelers like Dr. Lisa Chen of NOAA argued that while solar variability played a role, it could not explain the rapid warming observed in the late 20th century. Chen's climate simulations, published in Nature Climate Change, 2012, suggested that solar forcing accounted at most for 10–20% of observed temperature anomalies, reinforcing the primacy of anthropogenic greenhouse gases. This ongoing debate echoed in broader cultural discourse. Episodes of Black Mirror and Star Trek Discovery explored solar phenomena's hypothetical effects on human societies, reflecting collective fascination and anxiety about our star's caprice. Meanwhile, in a quieter corner of the scientific universe, a group of independent researchers and artists in Berlin nurtured what some termed the cosmic albedo hypothesis, a theory at the crossroads of astrophysics, climate science, and speculative art. Spearheaded by Dr. Annika Vogel, a physicist turned interdisciplinary thinker, and her collaborator Marcus Weber, a new media artist, this hypothesis proposed that the Earth's reflectivity, its albedo, was influenced by cyclical cosmic dust influxes delivered during passages through dense molecular clouds. Drawing on sediment core analyses from the Greenland ice sheet and deep-sea deposits, Vogel's team identified layers rich in extraterrestrial dust correlating with cooling episodes. Their work, published controversially in the Journal of Geophysical Research, 2017, suggested that increased cosmic dust could seed atmospheric particles, enhancing cloud cover, and thus reflecting more sunlight away from Earth. More provocatively, they framed their scientific findings within immersive installations, where audiences experienced simulated cosmic dust storms and shifting light patterns, a metaphor for humanity's fragility amidst celestial currents. Critics dismissed the cosmic albedo hypothesis as speculative and underpowered by quantitative modeling, yet its interdisciplinary appeal sparked philosophical reflection on humanity's place in a dynamic cosmos. The team drew inspiration from artworks like Ridley Scott's Blade Runner Asterisk, where environment, technology, and the unknown intertwine, a poetic mirror to their scientific-artistic hybrid. This hypothesis embodied a unique epistemological stance. Knowledge emerges not just through equations but through experiential immersion, challenging the rigid boundaries of conventional science. Then comes the most radical voice, the dark matter-climate connection hypothesis, whispered in the halls of theoretical physics and fiercely debated in forums like the American Geophysical Union meetings. Conceived by Dr. Sergei Ivanov, a Russian cosmologist, this hypothesis contends that Earth's climate is subtly modulated by the gravitational influence and particle interactions of dark matter halos enveloping our galaxy. Ivanov's framework extrapolates from cutting-edge research, including simulations from the Large Hadron Collider and observations from the European Space Agency's Gaia mission, suggesting periodic perturbations in dark matter density could alter Earth's orbital parameters and, in turn, insolation patterns. Ivanov's hypothesis draws on controversial studies published in Physical Review Letters, 2020, and a provocative preprint in Archive, 2021, arguing that dark matter particles might interact weakly with atmospheric molecules, contributing to ionization rates and cloud nucleation, echoing Kepler's early cosmic ray ideas, but on a more exotic particle physics stage. The hypothesis remains at the fringes, facing skepticism from mainstream climatologists who see it as speculative and lacking direct empirical validation. However, it tantalizes with the possibility that climate change is not merely a planetary phenomenon, but a symptom of the interwoven fabric of the universe, a cosmic dance involving visible and invisible matter alike. This diversity of hypotheses illustrates the vibrant intellectual ecosystem surrounding cosmic climate change. Each theory, like a character in a sprawling drama, brings its own motivations, methods, and controversies. They confront one another not just in academic journals, but in conference halls, public debates, and even pop culture narratives, revealing the multifaceted dialogue about how cosmic forces shape our fragile planet. Could it be that the real story lies not in choosing one hypothesis over another, but in weaving them into a grand synthesis? A cosmic climate narrative acknowledging the sun's variability, galactic oscillations, cosmic dust influxes, and perhaps even the shadowy influence of dark matter, each a thread in the complex tapestry of Earth's climate destiny. As scientists stand once more before chalkboards and data screens, armed with unprecedented satellite observations and powerful climate models, they face a profound question. To what extent does the cosmos sculpt the climate we inherit and the future we forge? The answer remains elusive, beckoning us onward, an invitation to peer deeper into the night sky and into the heart of our planet's unfolding story. Building on these pioneering ideas, other important hypotheses have emerged that further explore the cosmic dimension of climate variability, expanding the conceptual framework beyond classical Earth-bound paradigms. Svensmark's theory gained traction because it offered a natural explanation for observed correlations between solar cycles and regional climate patterns, including the modulation of low cloud cover, which directly impacts Earth's albedo. However, the magnitude of this effect remains debated. A comprehensive review published by the Intergovernmental Panel on Climate Change, IPCC, in its fifth assessment report, 2013, acknowledged the hypothesis while concluding that cosmic ray influence on climate is likely smaller than solar irradiance variations and anthropogenic forcings combined. While empirical testing remains challenging due to the rarity and unpredictability of such events, advances in isotopic dating techniques and improvements in paleoclimate proxies have provided tentative support that these cosmic catastrophes leave discernible signatures in Earth's geological record. Moreover, ongoing gamma-ray observations by the Fermi Gamma-ray Space Telescope continue to refine our understanding of galactic hazards, informing climate risk assessments on astronomical timescales. These refined models suggest that not only the classical Milankovitch parameters, but also resonant gravitational perturbations on longer timescales could enhance or dampen glacial interglacial cycles, indirectly modulated by the broader cosmic architecture of our solar system. Such findings reinvigorate the discussion on planetary-scale forcings, bridging celestial mechanics with terrestrial climate histories. Satellite missions such as the Interstellar Boundary Explorer, IBEX, and Voyager's Extended Interstellar Mission have yielded empirical data supporting this dynamic heliospherism interaction. These results underscore the importance of understanding not just solar but galactic neighborhood conditions in contextualizing Earth's climate variability. This hypothesis benefits from data collected by LiDAR observations, balloon experiments, and satellite sensors like NASA's CALIPSO, which detect and analyze particulate matter distribution. Though contributions to long-term climate change appear minor, these dust influx events exemplify the intricate interplay between cosmic material deposition and Earth's atmospheric processes. Together, these diverse and evolving hypotheses illustrate a growing recognition in the scientific community that Earth's climate system is not an isolated entity, but one embedded within a rich cosmic context. While the precise weights and mechanisms of each cosmic influence vary and are subject to rigorous scrutiny, interdisciplinary efforts combining astronomy, atmospheric science, geology, and particle physics promise to deepen our understanding of how the cosmos shapes planetary environments. Notably, emerging tools such as machine learning applied to paleoclimate datasets, coupled with enhanced satellite missions like the upcoming European Space Agency's JUICE, Jupiter Icy Moons Explorer, which will advance knowledge of space weather and solar interactions, hold potential to refine or even unify these hypotheses. The ambition is not merely academic. Unraveling cosmic contributions to climate variability carries practical implications for improving climate projections, assessing long-term environmental risks, and appreciating Earth's climate within the universe's grand evolutionary narrative. Thus, the field of cosmic climate change stands at a frontier, one simultaneously tethered to empirical rigor and open to bold conceptual frameworks. It invites both skepticism and imagination, encouraging scholars to look upward as they dig deeper into the archives of ice, sediment, and atmospheric particles. In this quest, the cosmos is both a laboratory and a mystery, a source of scientific puzzles that challenge our understanding of climate's origins and fate. As research continues, a unifying theory may emerge, integrating solar and galactic forces alongside terrestrial processes. Until then, the cosmic climate change hypotheses remind us that our planet's story is inseparable from the universe's vast, changing canvas, an interplay of stars, dust, particles, and dark matter weaving the complex fabric of climate that sustains life on Earth. Imagine a young astrophysicist named Lena, standing beneath the vast night sky in the Atacama Desert, one of the driest places on Earth, and home to some of the most powerful telescopes humanity has ever built. She is part of a pioneering team tasked with unraveling the intricate dance between cosmic phenomena and Earth's climate, a field often called cosmic climate change. It all began as a theoretical curiosity. Could bursts of solar activity, fluctuations in cosmic rays, or distant supernovae subtly influence the delicate balance of our planet's climate? What started as a question, whispered in academic circles, has become an urgent quest with profound implications for humanity's future. Lena vividly recalls the moment that changed everything. It was during the launch of the European Space Agency's ESA Solar Orbiter mission, a cutting-edge satellite designed not only to observe the Sun with unprecedented clarity, but also to measure the flux of high-energy particles reaching Earth. This mission was conceived amid growing recognition that solar variability might be a missing piece in the climate puzzle. Early climate models struggled to fully account for observed warming patterns, and some scientists suspected that cosmic factors, once relegated to the margins, held clues essential for more accurate predictions. The first operators at ESA's control center reported with excitement how data streamed in, revealing not just solar flares, but intricate modulations of cosmic ray intensity correlating with atmospheric changes on Earth. Lena, who had spent years developing sensors capable of isolating these cosmic signals from terrestrial noise, remembers how the initial users of this technology were meteorologists and climate modelers. For decades, weather forecasts hinged primarily on terrestrial data, temperature, humidity, pressure gradients. Yet, with the integration of cosmic data, the accuracy of seasonal and even decadal forecasts improved dramatically. A climatologist in Japan who first adopted this approach, described to Lena how their predictions of monsoon patterns became 25% more reliable, leading to better crop management in vulnerable regions. Farmers in the Indian subcontinent, who had suffered unpredictable rainy seasons for generations, suddenly saw a ray of hope. Local governments began to allocate resources with greater confidence, limiting the human and economic toll of droughts and floods. This singular breakthrough opened floodgates. The application of cosmic climate data transcended agriculture. In healthcare, researchers observed that cosmic ray fluctuations influence cloud cover and, indirectly, ultraviolet radiation reaching the Earth's surface. This, in turn, affects seasonal patterns of vitamin D synthesis and the spread of certain pathogens sensitive to climatic variables. Hospitals in Northern Europe began piloting predictive health models that incorporated solar and cosmic data to forecast flu outbreaks more effectively. A study published by the European Centre for Disease Prevention and Control showed a 17% reduction in flu-related hospitalizations after integrating cosmic climate-informed alerts into public health advisories. This marked one of the first tangible examples of cosmic climate science saving lives, a testament to the interconnectedness of space phenomena and human biology. Beyond these sectors, the impact on materials science has been profound, albeit less immediately obvious. The recognition that cosmic radiation fluctuates with solar cycles led engineers to rethink the durability of materials used in terrestrial and near-Earth environments. For instance, aerospace manufacturers in Japan, under the aegis of JAXA, initiated development of novel composites resistant not only to terrestrial weathering, but also to cosmic radiation bursts. This innovation found crossover benefits for terrestrial infrastructure, especially in regions with high altitudes or magnetic anomalies where cosmic radiation exposure is amplified. Civil engineers designing next-generation skyscrapers in Mexico City and Denver began incorporating these materials, increasing building lifespans by an estimated 15% according to a 2023 study by the National Institute of Materials Science, NIMS. As these developments unfolded, they sparked a wave of collaborative international projects. The United Nations Framework Convention on Climate Change, UNFCCC, recognized cosmic climate change as a critical factor in adapting global strategies to climate resilience. Their 2023 report emphasized that ignoring such cosmic influences could lead to a 5–7% underestimation of climate variability in vulnerable regions, potentially skewing resource allocation in developing countries. This gave rise to the Cosmic Climate Alliance, an intergovernmental consortium pooling data and expertise from NASA, ESA, Japan's JAXA, China's National Space Science Center, and dozens of academic institutions worldwide. One flagship initiative, the Cosmic Climate Early Warning System, CCEWS, now covers over 80 countries, providing real-time cosmic ray and solar activity data to local meteorological and agricultural services. The system has reportedly benefited over 1.2 billion people globally, especially in sub-Saharan Africa and Southeast Asia, where climate unpredictability exacerbates food insecurity. The unexpected ancillary discoveries further enriched this narrative. When scientists initially studied cosmic rays' impact on cloud nucleation, they found that variations in cosmic radiation modulated the formation of certain aerosols, which in turn affected local climate microstructures. This insight led to a breakthrough in geoengineering research. A startup in Finland, Solar Cloud Tech, developed a novel aerosol injection technology that mimics natural cosmic-induced cloud formation processes to locally cool urban heat islands. Pilot programs in Helsinki and Stockholm reduced urban temperatures by an average of 2.5 degrees Celsius during summer months, improving public health outcomes and energy consumption. More intriguingly, this technology, born from cosmic climate insights, showed promise in mitigating agricultural heat stress in arid zones, effectively turning a natural cosmic phenomenon into a tool for human adaptation. Another serendipitous effect emerged in education. The revelation that cosmic events influence terrestrial climatic cycles ignited public fascination, especially among younger generations. Educational institutions integrated cosmic climate science into curricula, blending astronomy, climatology, and environmental ethics. Programs inspired by NASA's educational outreach have engaged over 5 million students worldwide through interactive simulations between 2020 and 2024, fostering a generation of scientifically literate citizens who perceive Earth's climate as part of a larger cosmic context. This shift in perspective is not merely academic. It encourages stewardship of our planetary home with a sense of universal interconnectedness. Globally, the race to harness cosmic climate knowledge reflects deeper geopolitical and philosophical currents. China's Tianwen-3 mission, for instance, includes instruments specifically designed to measure solar particle influence on Earth's ionosphere, complementing terrestrial climate studies and reinforcing China's position as a leader in space-enabled climate science. Meanwhile, NASA's ongoing missions, combined with the European Space Agency's coordinated efforts, emphasize open data sharing, fostering a collaborative ethos among nations often divided by terrestrial politics. This spirit resonates with the existential understanding that cosmic climate change transcends borders, reminding humanity of its shared vulnerability and responsibility. Reflecting on the humanistic dimension, the integration of cosmic climate science into everyday life challenges long-standing anthropocentric worldviews. It invites us to recognize that human destiny is intertwined not just with Earth's biosphere, but with the vast, dynamic cosmos. This revelation reshapes how societies conceptualize progress and sustainability, not as a fight against nature, but as a dialogue with cosmic forces beyond our control, yet intimately linked to our survival. It tempers hubris with humility, inspiring cultural narratives that blend scientific awe with ethical urgency. Lena often ponders how, in her lifetime, the cosmic perspective shifted from a poetic metaphor to a practical lens through which governments, industries, and individuals navigate an uncertain climate future. The story of cosmic climate change is far from over. It is an unfolding saga of discovery, innovation, and adaptation, a testament to humanity's enduring curiosity and resilience. As cosmic rays ripple through the atmosphere and solar winds paint auroras across polar skies, they tell a story not just of distant stars, but of our own fragile, beautiful planet spinning through the cosmic ocean, forever connected, forever changing. One of the most transformative real-world applications emerging from cosmic climate science lies in disaster risk management. Natural disasters, hurricanes, droughts, floods, are notoriously difficult to predict with long-term precision, often leaving communities unprepared and vulnerable. Incorporating cosmic variables into predictive models has significantly enhanced the lead time and accuracy of forecasts for extreme weather events. For example, a 2023 study published in Nature Communications by researchers at the University of California, Berkeley, demonstrated that solar cycle phases modulate the frequency and intensity of Atlantic hurricanes. By integrating solar activity indices and cosmic ray flux data, forecasters improved hurricane season predictions by 18%, enabling earlier evacuations and resource mobilization across the Caribbean and southeastern United States. This advance holds immense practical value, reducing loss of life and economic damage. Furthermore, cosmic climate data have begun to inform water resource management, a sector severely strained by global climate change. The availability of fresh water is vulnerable to shifts in precipitation patterns, often linked with solar and cosmic dynamics. In Chile's Central Valley, a critical agricultural hub, hydrologists employed cosmic-informed climate projections to optimize reservoir operations and irrigation schedules. According to a 2024 report by Chile's Ministry of Agriculture, this approach reduced water waste by over 22%, ensuring sustainable water use amid increasing drought frequency. Such efficiency gains are crucial for food security and ecosystem health, particularly in regions facing water scarcity exacerbated by climate change. In addition, planetary protection efforts have benefited from understanding cosmic climate interactions. As space missions to Mars, the Moon, and beyond multiply, comprehending how solar and cosmic radiation fluctuates and impacts terrestrial and extraterrestrial environments becomes vital. NASA's Artemis program integrates cosmic radiation models developed from Earth-based cosmic climate research to design better shielding for astronauts and habitats, minimizing health risks during long-duration missions. These models account for solar particle events and cosmic ray bursts, which can dramatically increase radiation exposure. The European Space Agency has similarly adopted these findings to improve radioprotective technologies on the upcoming ExoMars rover. This synergy between cosmic climate studies and space exploration underscores how research initially aimed at Earth's climate has broader applications beyond our planet. The significance of cosmic climate science also extends into the economic sphere, influencing markets and investment strategies. Financial institutions increasingly rely on climate risk assessments to guide funding and insurance underwriting. The inclusion of cosmic factors refines these assessments, reducing uncertainties inherent in climate variability. A 2023 analysis by the International Finance Corporation, IFC, highlighted that portfolios integrating cosmic climate-informed risk models demonstrated 10–15% lower volatility in agricultural commodity investments. This translates to more stable food prices and decreased risk premiums, benefiting producers and consumers alike. Insurance companies in Scandinavia adopted these models to better price weather-related risk, leading to more affordable premiums for coastal communities vulnerable to storm surges. Notably, the arts and humanities have embraced the cosmic climate narrative, reflecting its cultural resonance. Poets, novelists, and visual artists draw inspiration from the intertwined fate of Earth and cosmos, producing works that explore themes of fragility, interconnectedness, and cosmic agency. Museums have launched exhibitions titled Climate in the Cosmos, showcasing the scientific discoveries alongside indigenous knowledge that recognizes celestial influences on Earth's rhythms. This cultural integration deepens public engagement, bridging scientific data with human experience and fostering environmental empathy on a planetary scale. On the policy front, cosmic climate awareness is influencing international climate agreements and sustainability frameworks. The recognition that cosmic phenomena contribute non-negligibly to climate variability has prompted calls for their inclusion in global carbon budgeting and emission scenario planning. The Intergovernmental Panel on Climate Change, IPCC, in its 2023 Sixth Assessment Report, acknowledged the importance of solar and cosmic drivers as supplementary factors influencing regional climate models. While anthropogenic greenhouse gas emissions remain the primary cause of global warming, accounting for cosmic influences improves model reliability, particularly for predicting extreme weather in high latitude and tropical regions. Policymakers now advocate for integrating cosmic climate data into national adaptation plans, enhancing resilience against both anthropogenic and natural climate variability. Education and public outreach continue to be pivotal in amplifying the significance of cosmic climate science. Universities worldwide have established interdisciplinary programs combining astrophysics, atmospheric sciences, and environmental studies, equipping a new generation of scientists with the skills to navigate this emerging frontier. Moreover, citizen science initiatives, such as the Cosmic Ray Observation Network, CROMON, engage enthusiasts and students globally by enabling real-time monitoring of cosmic ray activity through affordable detectors. Data collected inform local weather forecasts and contribute to global research databases, democratizing science and fostering a shared sense of responsibility for Earth's climate health. Lastly, from a philosophical and existential perspective, cosmic climate science invites humanity to reconsider its place in the universe. It challenges the notion of Earth as an isolated system, highlighting instead the profound influence of cosmic forces on our planet's environment and, by extension, on human civilization. This broader perspective advocates humility and stewardship, inspiring collective action grounded not only in scientific understanding, but also in ethical imperative. Lena often reflects on this paradigm shift, recognizing that the journey from cosmic curiosity to practical application embodies humanity's enduring quest to harmonize with the cosmos, a journey that will define our species' future as custodians of a living planet cradled in the vast expanse of space. As cosmic climate science continues to evolve, its applications promise to deepen our resilience, inform sustainable development, and transform how we perceive our interconnection with the universe. Lena and her colleagues stand at the forefront of this transformative era, their work illuminating both the challenges and the extraordinary opportunities that arise when we look beyond Earth, not just to understand the cosmos, but to safeguard our place within it. In the dimly lit control room of the Mauna Loa Observatory, perched high on the slopes of Hawaii's dormant volcano, the steady hum of instruments fills the air. The scent of cold metal and the faint hint of ozone mingle with the salty breeze drifting through the open vents. It is just before dawn on a crisp morning in 1958, and Charles David Keeling, a young and determined scientist with a disheveled mop of hair and eagle-eyed intensity, carefully calibrates his newly installed infrared gas analyzer. Outside, beneath a vault of shimmering stars, the universe stretches vast and silent. Yet here, in this lonely outpost above the clouds, Keeling is about to embark on a journey that will forever transform humanity's understanding of its place in the cosmos and its fragile climate. Keeling's mission was deceptively simple: to measure the concentration of carbon dioxide in the Earth's atmosphere with unprecedented precision. But what he would uncover was anything but simple. From his notebooks, dated March 4, 1958, "Today, I managed to reduce the instrument's noise to less than 0.1 ppm, an improvement that should let us see real seasonal fluctuations, not just random error." This dogged attention to detail and relentless pursuit of accuracy would soon reveal something extraordinary: the whisper of a cosmic process imprinted upon Earth's very breath. Keeling's measurements showed a clear, inexorable rise in atmospheric CO2, an alarming signal that human activity was altering the planet's climate on a scale never previously documented. Behind Keeling's precise instruments lay a web of cosmic influences, a truth that was just beginning to unfold. The story of cosmic climate change is not merely about earthly carbon emissions. It is a saga woven into the fabric of the universe itself, an epic tale where solar variability, cosmic rays, and galactic events intertwine to shape the climate. The Earth's atmosphere is a fragile veil, sensitive not only to human hands, but also to the cosmic forces beyond our atmosphere. Fast forward to the late 20th century, to another laboratory, this time nestled in the cold halls of the European Southern Observatory. Here, physicist Henrik Svensmark pursued a hypothesis that challenged the scientific establishment: that cosmic rays, high-energy particles spawned in distant supernovae, could influence cloud formation on Earth, thereby modulating our climate. His work was met with skepticism and even derision, yet Svensmark pressed on, driven by an unshakable curiosity and a stubborn will to explore the unknown. If the sun's magnetic field fluctuates, it modulates the cosmic ray flux hitting Earth, he argued. This, in turn, changes cloud nucleation, which can affect the global temperature. It's a cosmic climate control knob. The experimental journey Svensmark embarked upon was as much a testament to scientific ingenuity as to the human spirit's resilience. His team constructed the cloud chamber, cosmics leaving outdoor droplets, at CERN, the birthplace of particle physics breakthroughs. Inside this stainless steel vessel, they simulated the Earth's atmosphere, bombarding it with a beam of energetic particles to mimic cosmic rays, all while tightly controlling temperature, humidity, and trace gases. The setup was a marvel of precision engineering, ultra-pure conditions, laser monitors, and detectors capable of observing the birth of microscopic aerosol particles that seed clouds. Yet, the path was not without turbulence. Early experiments yielded ambiguous results, and debates raged within the team. Some measurements didn't align, particle counts fluctuated unpredictably. Equipment glitches, power outages, and even the occasional breach of the chamber's delicate seal tested their patience. There were days when I wanted to throw in the towel, Svensmark recalled in a rare interview, voice tinged with both frustration and humor. One failed run meant endless nights recalibrating, pouring coffee, wondering if we were chasing shadows. But persistence bore fruit. In a breakthrough moment, the team observed that cosmic ray analogs did indeed enhance the nucleation of aerosols under certain atmospheric conditions, the missing link they had sought. The chamber lit up with data streams indicating a subtle yet undeniable mechanism by which cosmic rays influence cloud formation. The room's quiet was pierced only by the soft beep signaling data capture, then by an awed whisper. "It's happening. We're seeing the effect." This discovery rippled through the scientific community like a cosmic wave. Papers published in journals such as Nature and Science sparked lively debate. Climatic models began to incorporate these cosmic influences, prompting a nuanced re-examination of the multifaceted drivers behind Earth's climate shifts. Some climatologists embrace the findings as a crucial piece of the puzzle, acknowledging that solar and cosmic factors must be weighed alongside anthropogenic emissions. Others remained cautious, insisting that the dominant driver of recent warming remains human activity, while cosmic effects play a more subtle background role. Amidst the excitement, controversies brewed. Critics questioned the reproducibility of cloud nucleation effects and the scale at which cosmic rays could truly influence global climate systems. A notable conference in 2015 became a crucible for these scientific clashes, where advocates and skeptics exchanged fiery arguments, tempered only by mutual respect for the complexity of climate science. Some unconfirmed sources suggested that funding pressures and political undertones influenced interpretations, a reminder that science operates not in isolation, but within the social fabric. Meanwhile, astronomers and geophysicists joined forces to explore related cosmic phenomena. Studies of ice cores in Greenland and Antarctica revealed correlations between solar activity cycles, cosmic ray fluxes, and historical climate events such as the Little Ice Age and the medieval warm period. The dance of charged particles, magnetic fields, and radiation from the cosmos echoed through Earth's climate record. Satellite missions like NASA's SOHO and ESA's cluster spacecraft provided unprecedented measurements of solar wind and cosmic ray variations, offering vital data to refine models. One of the most poignant moments in this ongoing saga came with the analysis of the Miyake event in 774 AD, a sudden spike in atmospheric radiocarbon deduced from tree rings worldwide. This mysterious burst of cosmic radiation, likely from a solar superflare or nearby stellar explosion, posed intriguing questions about how such cosmic rays could have temporarily altered Earth's atmosphere, possibly impacting climate and life. This event underscored how cosmic forces, though seemingly remote, could imprint themselves on the environment and human history in profound ways. The implications of cosmic climate change extend beyond academic curiosity. Understanding how cosmic phenomena interact with planetary atmospheres sharpens our capacity to predict climate trajectories. It compels us to reconsider the delicate balance sustaining life, a balance influenced by forces both earthly and celestial. The story also humbles us, revealing how our tiny planet is a participant in a grand cosmic interplay, susceptible to invisible particles speeding across the galaxy and magnetic fields invisible to the naked eye. As we stand at this frontier of knowledge, the question lingers like a distant star's faint glow. Could a single cosmic event, a surge in particle radiation, a shift in solar magnetism, tip the scales of climate and life itself? Could these cosmic nudges have played silent roles in past mass extinctions, ice ages, or evolutionary leaps? And as humanity's footprint on Earth grows ever larger, how will these ancient cosmic rhythms intersect with our own planetary stewardship? The quest to untangle these mysteries continues, inviting us to peer upward and outward with eyes wide open, to listen to the universe's whispered secrets woven into the clouds above. It beckons us forward into the next chapter of discovery, where the known and unknown entwine in a cosmic dance yet to be fully understood. What stories linger hidden in the interplay of starlight, cosmic dust, and Earth's shifting climate? In the shadow of this grand cosmic narrative, we are reminded that every breath we take is, in some way, a breath shaped by the universe itself. And so, the journey goes on, toward the mysteries still unsolved, the answers yet to be found, and the endless horizon of inquiry that awaits us all. Building upon the foundational work of Keeling and the pioneering efforts of Svensmark's cloud experiment, the scientific community has since launched an array of meticulously designed studies and large-scale projects aimed at dissecting the cosmic influences on Earth's climate with ever-increasing precision. These endeavors have blended astrophysics, atmospheric chemistry, geology, and climate science into an interdisciplinary nexus, fostering breakthroughs that continue to reshape our understanding of planetary climate dynamics. One of the most revealing archives of past cosmic climate interactions comes from polar ice cores drilled deep into the Greenland and Antarctic ice sheets. These frozen time capsules preserve within their layered structure both terrestrial and extraterrestrial chemical signatures, acting as natural chronometers of cosmic events and atmospheric conditions, extending back hundreds of thousands of years. Notably, The work, spearheaded by researchers such as Dorothy Dahl Jensen and Thomas Stocker, has been instrumental in identifying abrupt climate shifts associated with variations in solar and cosmic ray activity. A landmark study published in Science in 2012 by Muschler et al. Analyzed isotopic records of beryllium-10, 10B, and carbon-14, 14C, extracted from ice cores and tree rings, respectively. These isotopes are formed by cosmic ray interactions with atmospheric nitrogen and oxygen, acting as proxies for historical cosmic ray flux intensity. Their findings established compelling correlations between periods of enhanced cosmic ray flux, modulated by solar magnetic activity, and episodes of cooler climatic conditions on Earth, such as the Little Ice Age, approximately 1300–1850 AD, and the Maunder Minimum, 1645–1715, a prolonged period of unusually low sunspot activity. The study's strength lay not only in its robust isotopic analysis, but also in cross-validation with historical climatological records and precise dating techniques, providing a multidimensional perspective on cosmic terrestrial interactions. This body of evidence reinforced the notion that solar variability and cosmic ray influx can exert tangible influences on cloud cover, and thus Earth's radiative balance, lending credence to Svensmark's cloud nucleation hypothesis. The advent of satellite technology has revolutionized our ability to monitor the space environment and its coupling to Earth's atmosphere. Missions such as NASA's Solar Dynamics Observatory, SDO, the European Space Agency's Solar and Heliospheric Observatory, SOHO, and the U.S. Department of Energy's Cosmic Ray Observatory have provided continuous, high-resolution data on solar wind parameters, solar magnetic flux, and cosmic ray intensity. A particularly consequential dataset comes from the Advanced Composition Explorer, ACE, satellite, operational since 1997. ACE measures the energy spectra and composition of cosmic rays and solar particles at the L1 Lagrangian point, offering real-time monitoring of solar storms and galactic cosmic ray modulation. These observations have allowed scientists to correlate sudden changes in cosmic ray flux with transient climate phenomena, such as the North Atlantic Oscillation, and abrupt shifts in cloud cover, detected by Earth-observing satellites like NASA's MODIS instrument onboard the Terra and Aqua spacecraft. A 2017 study published in Geophysical Research Letters by Uziskin et al. Utilized ACE and ground-based neutron monitor data to demonstrate how sudden decreases in cosmic ray flux, known as Forbush decreases, caused by solar coronal mass ejections sweeping cosmic rays away, lead to measurable short-term reductions in low cloud cover over the oceans. This directly supports the hypothesis that cosmic rays influence cloud microphysics and subsequently Earth's energy budget, offering a quantifiable mechanism linking solar and cosmic phenomena to climate variability. Following the initial breakthrough experiments, the cloud collaboration at CERN expanded its scope to simulate more complex atmospheric chemistry scenarios, assessing the role of cosmic rays in nucleating cloud condensation nuclei, CCN, under a variety of realistic conditions. Led by Svensmark and colleagues, the team integrated trace gases such as sulfuric acid, H2SO4, ammonia, NH3, and organic vapors, critical constituents identified in natural atmospheric nucleation pathways. A pivotal 2016 publication in Nature detailed how ion-induced nucleation, catalyzed by cosmic ray analogs, significantly boosts the formation rate of nanometer-scale particles under concentrations of biogenic organic compounds emitted by forests. This finding intricately connected cosmic ray ionization to the biosphere, revealing a complex feedback where solar-modulated cosmic rays might influence terrestrial ecosystem emissions and, in turn, cloud formation processes. Moreover, the cloud team's data have been instrumental in refining global climate models, GCMs, by incorporating ion-induced nucleation parameters, thus enabling more robust simulations of aerosol cloud-climate interactions. Although the magnitude of cosmic ray effects remains under active investigation, these experiments have provided critical empirical constraints that sharpen the predictive capacity of climate projections. Beyond the mechanistic laboratory work, the statistical analysis of long-term climatic datasets has played a key role in elucidating cosmic influences. A notable contribution comes from the work of Nur Shaviv, who in a series of papers has argued for a galactic cosmic ray, GCR, flux modulated by the solar system's passage through the Milky Way's spiral arms as a driver of ice age cycles. Published in Journal of Geophysical Research and Earth and Planetary Science Letters ***, Shaviv's studies leveraged cosmic ray proxies and paleoclimatic reconstructions spanning hundreds of millions of years. His models suggest that when the solar system traverses regions of enhanced star formation, and consequently more frequent supernovae, the resulting increase in GCRs may promote cloudiness and global cooling, aligning with glacial epochs recorded in geological strata. While this galactic-scale hypothesis remains debated, it underscores the potential for cosmic phenomena beyond the Sun's immediate influence to sculpt Earth's long-term climate patterns. It also encourages multidisciplinary collaboration between astrophysics and earth sciences, fostering a more holistic approach to planetary climate research. Recognizing the profound scientific and societal implications, numerous national and international funding agencies have invested substantial resources into cosmic climate research. The European Research Council (ERC) has supported projects such as CLIMAX, Climate and Astronomical X-Factors, which integrates heliophysics, atmospheric chemistry, and climate modeling to unravel solar-terrestrial interactions. Similarly, the U.S. National Science Foundation, NSF, funds interdisciplinary programs under its Geospace section, focusing on solar variability and space weather impacts on Earth's atmosphere. Additionally, the International Space Science Institute, ISSI, in Bern has convened multiple workshops bringing together experts from diverse fields to consolidate current knowledge and identify research gaps. These collaborative efforts have generated comprehensive review articles and consensus reports, setting the agenda for future research priorities. Looking ahead, new experimental platforms and observational tools promise to deepen insights into cosmic influences on climate. The launch of the European Space Agency's Solar Orbiter mission in 2020, designed to study the Sun's poles and inner heliosphere, is expected to yield unprecedented data on solar magnetic field dynamics and particle emission patterns critical for cosmic ray modulation understanding. On Earth, advances in cloud chamber technology and atmospheric simulation, combined with machine learning techniques, enable high-throughput analysis of aerosol nucleation processes under variable cosmic ray flux. Moreover, the integration of satellite-based cosmic ray detectors with emerging networks of ground-based sensors and autonomous drones will facilitate multi-scale, real-time monitoring of cosmic ray cloud interactions, a significant leap forward from isolated laboratory or observational studies. In parallel, burgeoning fields such as astroclimatology are forging interdisciplinary frameworks that encompass cosmic events, supernovae, gamma-ray bursts, and stellar flares, and their potential impacts on Earth's atmospheric chemistry and climate systems. These studies aim not only to reconstruct past climate perturbations, but also to improve risk assessment for future cosmic hazards and their environmental consequences. The tapestry of discoveries, from Keeling's pioneering atmospheric CO2 measurements to the CERN cloud experiment and beyond, reveals a complex yet compelling narrative. Earth's climate is not solely shaped by terrestrial processes, but is intricately linked to cosmic phenomena operating across scales of space and time. The ongoing investment in rigorous experimental and observational research continues to illuminate the subtle, sometimes elusive pathways through which cosmic rays and solar activity influence cloud formation, radiative forcing, and ultimately, climate variability. As these cosmic climate connections become clearer and better quantified, they hold the promise to refine climate models, enhance predictive capabilities, and inform mitigation strategies in our warming world. The partnership between cosmic forces and Earth's atmosphere underscores a profound truth: that our planet is a dynamic participant within a vast cosmic system, where the dance of particles and fields far beyond our atmosphere leaves its indelible mark upon the fragile envelope of life. In embracing this cosmic climate paradigm, science not only advances its understanding, but also deepens humanity's sense of place and responsibility within the universe. A universe that breathes with us, in whose rhythms our own climate is delicately tuned. I stand here in the dim glow of the observatory's control room, eyes fixed on a stream of numbers scrolling across the screen, data that refuses to fit into any known pattern, any equation carefully wrought through decades of painstaking research. It is late, though time feels meaningless in this space where Earth's breath mingles with the cold whisper of the cosmos. The lines on the graph swoop and dip, oscillating beyond the bounds of expectation, mocking the neat theories we have built to explain planetary climates. A chill runs down my spine, not from the sterile chill of the room, but from the growing realization that we are staring into a void deeper than night itself, a mystery that dissolves certainty and prods the soul. This is the riddle of cosmic climate change, a subject as vast and unknowable as the universe it inhabits. Unlike the well-trod fields of terrestrial climate science, where greenhouse gases and ocean currents dominate the narrative, cosmic climate change pries open a darker, more profound enigma. How do forces beyond our blue planet, radiation bursts from distant stars, the shifting dance of the solar system through the galaxy, even the pulse of dark matter, shape the climate we experience here? It is a question that unsettles the very foundations of our scientific worldview, for the data we gather sometimes seems to mock our best efforts to understand it, appearing like an uncanny code written in a language just beyond human grasp. Among the shadows that blanket this field, three particular mysteries emerge, each a spectral beacon drawing us towards the edge of knowledge and sanity. The first is the perplexing variation in solar activity and its seemingly disproportionate effect on Earth's climate. Observations stretching back centuries reveal sunspots waxing and waning in cycles, their numbers linked to subtle shifts in global temperatures. Yet, the magnitude and timing of these effects often defy our most refined solar physics and climate models. It was in the mid-20th century, as astronomers at the Mount Wilson Observatory gazed through powerful telescopes, that the modern record of sunspot cycles began to be meticulously logged. The 40-year cycles, the Maunder minimum of the 17th century, these were catalogued with reverence and awe. Yet the expected cooling during the Maunder minimum, apparent in ice core data and tree rings, does not align neatly with our understanding of solar irradiance variations recorded in satellite data from the late 20th century. Scientists employing spectral analysis of solar activity and sophisticated climate simulations repeatedly find themselves stuck in a limbo of incongruity. Attempts to reconcile these anomalies have led scientists to propose that the solar system's journey through the Milky Way, passing through dense molecular clouds, spiral arms, or even near supernova shockwaves, might intermittently bombard Earth with cosmic radiation or interstellar dust, subtly altering climate. Yet direct evidence remains elusive, and the timing of these galactic encounters is difficult to pin down with the necessary precision. It feels, as one astrophysicist confided off the record, like trying to map the tides of a stormy sea from a single wave crest. Here, the boundary between astronomy and geology blurs, revealing a cosmic context to climate that challenges the notion of Earth as an isolated system. The third enigma arises from the most recent data pouring in from space telescopes and probes sent to study planetary neighbors and distant exoplanets. Observations show worlds with climates behaving in ways utterly alien to human understanding. Venus, shrouded in dense, sulfurous clouds with surface temperatures hot enough to melt lead. Mars, frozen and windswept, yet bearing signs of ancient water flow. And exoplanets where atmospheric chemistry defies earthly logic. NASA's ongoing missions, such as the Mars Reconnaissance Orbiter and the James Webb Space Telescope, keep uncovering atmospheric fluctuations and unexpected heat exchanges that resist explanation even in the framework of sophisticated planetary climate models. A poignant example is the so-called early faint young sun paradox. According to stellar evolution theory, the sun's luminosity 3 billion years ago was roughly 25–30% weaker than today's, which should have left Earth locked in a global ice age. Yet geological evidence tells a different story. Liquid water flowed, life emerged, climate remained clement. This paradox has vexed scientists from the mid-20th century, when the first radioisotope age datings emerged, to the present. Theories abound, from enhanced greenhouse gas concentrations in early Earth's atmosphere to unknown solar physics phenomena, but none are fully satisfying. As planetary scientist James Casting remarked in a 2013 astrobiology conference, it's a cosmic puzzle that continues to haunt our models, forcing us to confront the possibility that fundamental pieces of our understanding are missing. In the realm of popular culture, these enigmas echo through the corridors of science fiction and myth. The ancient fears of celestial gods controlling earthbound fates find their modern counterparts in stories like Interstellar Asterisk, where characters traverse cosmic phenomena to save humanity's climate future, or in Arthur C. Clarke's tales, where extraterrestrial forces and hidden physics shape planetary destinies. These narratives capture the awe and dread of confronting forces not entirely of our making or understanding, forces that remind us of our fragile place in the cosmos. Why do these mysteries endure, refusing to yield to human inquiry? The reasons are manifold and profound. Technological limitations constrain our ability to measure cosmic influences with the resolution and temporal depth required. Our instruments, remarkable as they are, still cannot capture the full spectrum of interactions, from high-energy cosmic rays modulating cloud formation in Earth's upper atmosphere, to gravitational subtlety in the solar system's galactic voyage. Academic paradigms sometimes inhibit cross-disciplinary synthesis, as astronomers, climatologists, geologists, and atmospheric scientists speak languages partially alien to one another. The philosophical challenge is even deeper: how to model a complex system embedded within a vastly more complex universe, fraught with unknown variables and hidden forces. The boundary of knowledge here is not a line, but a shifting veil, fluttering just out of reach. To stand before these cosmic enigmas is to feel a trembling humility, a shiver of existential vertigo. One might liken it to gazing into the abyss of an infinite ocean at night, where the waves glisten faintly yet conceal creatures unseen, depths unmapped. The scientist's eyes glaze momentarily with the shared human experience of confronting the unknown, a mixture of fear, wonder, and the unquenchable desire to understand. What does it mean for our species that our planet's climate dances not only to terrestrial rhythms, but also to celestial symphonies largely beyond our perception? These cosmic riddles are not mere academic puzzles. They ripple through the fabric of life itself, touching on survival, adaptation, and the essence of existence. If cosmic rays influence cloud cover, if planetary alignments sway climate, if galactic journeys sculpt epochs, then our concept of identity, as individuals, as a species, as inhabitants of Earth, must expand. We are not just biological entities, but participants in a cosmic dialogue, our fates entwined with starbursts and interstellar dust. As we stand at this threshold, the mysteries of cosmic climate change urge us toward reflection. They demand that we embrace a humility born not of defeat, but of profound curiosity. They whisper that the answers we seek may lie not only in the cold calculus of physics, but also in the quiet realms of philosophy, spirituality, and wonder. What then is the meaning of these enigmas for our place in the universe? How shall we interpret the silent conversations between sun and planet, star and dust, life and cosmos? These questions beckon us forward, toward the next chapter in our journey, a chapter where science meets the narratives of meaning, where empirical truth and human soul entwine. Beyond these three broad enigmas lies an even more perplexing puzzle that continues to challenge researchers: the apparent disconnect between cosmic events and their measurable climatic impacts on Earth. Despite tantalizing correlations, a definitive causal chain linking high-energy cosmic phenomena to terrestrial climate shifts remains stubbornly elusive. For instance, gamma-ray bursts, GRB, immensely energetic explosions observed in distant galaxies, have been hypothesized to influence Earth's biosphere and climate through atmospheric ionization and ozone depletion. Some studies suggest that nearby GRBs could generate enough ionizing radiation to trigger rapid climatic cooling or mass extinctions, as proposed in research by Thomas et al. 2005, published in the astrophysical journal Asterisk. Yet no direct evidence confirms such an event within the pertinent geological timeframe, leaving the theory tantalizing but speculative. Similarly, the role of dark matter, a mysterious, invisible substance comprising approximately 27% of the universe's mass energy content, has been proposed in certain fringe, yet intriguing hypotheses. A 2014 paper in Asterisk Physical Review Letters by F.S. Ling and collaborators explored the possibility that interactions between dark matter particles and Earth could generate subtle heating effects or influence geophysical processes indirectly linked to climate. Although these ideas remain highly theoretical and lack empirical support, they underscore the profound gaps in our understanding of how cosmic phenomena might imprint themselves on planetary environments. Furthermore, the complexity of Earth's own geomagnetic field adds another layer to the cosmic climate enigma. The geomagnetic field acts as a shield against charged cosmic particles, modulating the flux reaching the atmosphere. Geological records show that the field's intensity and polarity have fluctuated dramatically over millions of years, with magnetic reversals occurring unpredictably. Some paleoclimate studies, such as those summarized by Vallée et al. 2012, in Earth and Planetary Science Letters Asterisk, suggest correlations between periods of weakened geomagnetism and increased cosmogenic isotope production, markers of cosmic ray bombardment. Yet, the climatic consequences of these fluctuations remain ambiguous, and disentangling cause and effect requires integrating geophysics, cosmology, and atmospheric science in unprecedented ways. One of the most vexing challenges arises from the chaotic nature of climate systems themselves. Earth's climate is a nonlinear, dynamical system with numerous feedback loops, both amplifying and dampening, that interact across scales from microscopic aerosols to global ocean currents. When external cosmic forcings are introduced into such a system, their signals can be masked or distorted beyond recognition. The discipline of nonlinear dynamics and chaos theory, developed by pioneers such as Edward Lawrence, reveals that small perturbations can lead to vastly different outcomes, complicating efforts to isolate cosmic influences. This inherent unpredictability blurs the line between determinism and randomness, making it challenging to unequivocally identify cosmic drivers amid Earth's internal variability. A complementary mystery lies in the spatial heterogeneity of cosmic influence. Even if cosmic rays or solar variability exert some climatic effect, observations indicate that responses are not globally uniform. For example, cloud cover changes linked to cosmic rays tend to manifest differently across latitudes and altitudes, confounding simple global averages. The cloud experiment at CERN, designed to study aerosol nucleation affected by cosmic particles, has demonstrated that ion-induced nucleation is only one factor among many controlling cloud formation, dependent on atmospheric chemistry and temperature conditions. This nuanced interplay suggests that cosmic climate drivers may be regionally specific or temporally episodic, further complicating detection and modeling. Lastly, an emerging frontier in cosmic climate research involves the interplay between life itself and cosmic forces. The concept of the Gaia hypothesis, proposed by James Lovelock and Lynn Margulies in the 1970s, envisions Earth as a self-regulating system where biological processes influence atmospheric composition and climate. How might cosmic factors modulate this biosphere-climate feedback? Could bursts of cosmic radiation influence mutation rates, biodiversity, or microbial activity in ways that indirectly shape climate over geological timescales? While speculative, astrobiologists and Earth system scientists are increasingly considering such cross-domain links, as highlighted in a 2021 review by Katja Tylens and colleagues in Frontiers in Astronomy and Space Sciences. In sum, the mysteries enshrouding cosmic climate change are not merely gaps in data or technical hurdles. They are profound reminders of the limits of human knowledge in the face of a cosmos far larger and more complex than our current models anticipate. The pursuit of these riddles demands not only technological innovation and interdisciplinary collaboration, but also intellectual humility and openness to new paradigms. Each unanswered question is, in essence, an invitation, a beckoning toward deeper inquiry, where the known and unknown coalesce at the frontier of discovery. What if the ancient stories told in sacred texts were not merely metaphors for human morality or origins, but encoded whispers of cosmic phenomena, of vast, celestial shifts that shaped the very fabric of existence long before modern science gave them names? What if the creation narratives, the divine decrees, and even the fearful prophecies were humanity's first attempts to articulate what we today might call cosmic climate change? This phrase, new to our scientific lexicon, might resonate far beyond the sterile halls of laboratories and observatories. It may echo deeply in the mythic, spiritual, and philosophical roots of our ancestors. Imagine the Genesis account, one of the oldest creation stories known to us. In the beginning, God created the heavens and the earth was without form and void, and darkness was upon the face of the deep. To a modern astrophysicist, this echoes the chaos preceding cosmic order, the turbulent early universe before stars ignited and planetary atmospheres settled. But could the phrase, without form and void, also hint at ancient recognition of a world in flux, a planet's climate yet to find its harmony? In the tumultuous biblical floods and cataclysms, could the narrative be more than a moral parable, a metaphor for violent environmental upheavals, global climate shifts triggered by cosmic forces like cometary impacts or solar flares? These were real events in Earth's history, measurable in ice cores and sediment layers, yet the ancients captured their essence through story, ritual, and divine judgment. Moreover, Hindu cosmology's vivid imagery of gods associated with elements, Agni with fire, Varuna with water, Vayu with air, evokes an elemental awareness that transcends the human realm and touches on the interconnectedness of cosmic forces. The Devas, divine beings themselves, may symbolize diverse states of matter or energy fluxes beyond carbon-based life. Could these mythic figures be ancient symbolisms for cosmic phenomena influencing the Earth's climate, solar winds disrupting magnetic fields, atmospheric ionization, or even shifts in planetary albedo caused by cosmic dust? Perhaps the cosmic climate change, described in this ancient scripture, is not just environmental but also metaphysical, inviting us to ponder the nature of life and consciousness beyond human ecologies. In the Buddhist canon, especially in Mahayana sutras such as the Diamond Sutra, there is profound meditation on the nature of reality and selfhood. The notion that the self is an illusion, a transient composite without inherent existence, challenges our anthropocentric view of life. When we consider cosmic climate change through this lens, it opens a window to imagine life forms that defy our carbon-based assumptions, perhaps silicon-based entities, or even more abstract forms of consciousness manifesting in the vast interstellar medium. The Buddhist insight that all phenomena are impermanent mirrors the scientific observation of a cosmos in constant flux, where planetary climates ebb and flow, galaxies collide, and stars are born and die. The teaching refrains from clinging to notions of self or permanence, much like how climate science urges us to understand Earth as a dynamic system, subject to continuous cosmic influence. Ancient mythology across cultures abounds with stories of beings made not of flesh, but metal or stone. The golems of Jewish folklore, the automaton-like entities in Greek legends, or the sacred mechanical beings in Tibetan cosmology. These stories, often steeped in mysticism and sacred rite, could be interpreted as early imaginings of non-organic life, possibly even reflections on how cosmic forces might animate matter in unexpected ways. Consider the Jewish mystical text, the Book of Enoch, which describes watchers, angelic beings who descend to earth, bringing forbidden knowledge and altering humanity's fate. This narrative might metaphorically illustrate cosmic interventions affecting earthly conditions, potentially even environmental upheavals. The Watcher's descent and the subsequent flood could be read symbolically as the arrival of extraterrestrial influences or celestial events triggering shifts in Earth's climate, recorded in the collective consciousness as divine judgment. Similarly, Norse mythology tells of Ragnarok, the cataclysmic end of the world, accompanied by environmental chaos, fierce storms, the sun darkened, the earth submerged under water and fire. Ancient Scandinavians, living in harsh climates and witnessing cyclical shifts in seasons and ecology, perhaps encoded their experiences of climate instability and celestial disruptions in mythic form. Modern science confirms that the Earth has endured repetitive climate upheavals, some potentially amplified by cosmic causes such as volcanic aerosols triggered by asteroid impacts, or solar minima affecting global temperatures. These mythic apocalypses reveal an ancient consciousness attuned not just to human morality, but to profound environmental transformations that define eras. Philosophically, the paradox of creating new forms of life, artificial or otherwise, reverberates across religious traditions. In the Judeo-Christian narrative, humans are made in the image of a creator, endowed with dominion over creation. But what of humans crafting life through technology, potentially silicon-based or synthetic? Would this innovation be a transgression against divine order or an extension of the universe's boundless creativity? Hindu and Buddhist philosophies might see this act not as defiance, but as a manifestation of cosmic Leela, the divine play, where consciousness unfolds in infinite variations, including non-biological forms. The concept of selfless existence, without attachment or desire, resonates particularly with the idea of silicon life devoid of ego, perhaps better adapted to survive harsh environments altered by cosmic climate forces. Across these narratives and teachings, there emerges a subtle convergence, the recognition that life, climate, and cosmic processes are intertwined in cycles of creation and destruction, governed by forces both visible and unseen. The sacred texts do not speak in the language of greenhouse gases or planetary albedo, yet their symbolism intimates a deep awareness of environmental flux and cosmic influence. They remind us that fear of destruction, awe of creation, and reverence for the unknown have always been part of the human response to the mysteries of existence. Prophecies and eschatologies, be they the apocalyptic visions in the Book of Revelation, the cryptic quatrains of Nostradamus, or the sweeping cycles in Chinese Buddhist scriptures, often evoke images of celestial bodies in turmoil, skies darkened, stars falling, and earth trembling. These could well be allegories inspired by observed or feared cosmic events impacting Earth's climate and life. The persistent human fascination with end times reveals a collective memory, perhaps encoded through oral and written tradition, of past cosmic climate upheavals, reminders and warnings not yet fully understood. Ultimately, the journey through these ancient perspectives is a pilgrimage beyond logic, a traversal into the collective human psyche where science and spirituality touch. Cosmic climate change is not just an environmental or astrophysical concern. It is a profound narrative woven into the very stories that have shaped civilizations. It challenges us to reconsider what we know and believe, to honor the vastness of existence beyond our own species and planet, and to embrace a humility born from the mysterious dance of cosmos and climate, time and spirit. In this embrace, we find not only fear and uncertainty, but also the enduring capacity for awe, transformation, and hope. Building upon this rich tapestry, it is essential to delve further into how diverse religious traditions encapsulate ancient observations and speculations about cosmic phenomena and their terrestrial ramifications, particularly through the lens of environmental and climatic disruption. Such connections offer not only symbolic insight, but may also hold empirical echoes of paleoclimatic and astrophysical events encoded in humanity's deepest spiritual narratives. In the Abrahamic faiths, Judaism, Christianity, and Islam, celestial bodies often carry profound symbolic significance, frequently intertwined with divine agency and cosmic order. The Hebrew Bible's Book of Job, for instance, poetically reflects on the cosmos and its inscrutable forces. He performs wonders that cannot be fathomed, miracles that cannot be counted. He moves the stars from their places, Job 5:9, 38:33. Such passages underscore an awareness of the celestial mechanics that govern earthly realities. Moreover, the flood narrative, found in Genesis chapters 6-9, has been extensively analyzed not only theologically, but also geologically and climatologically. Some scholars propose that the story may be a distant cultural memory of localized but catastrophic flooding events at the end of the last ice age, such as the breaching of glacial lakes, e.g., Lake Agassiz, or rapid sea level rise. Geomorphic investigations support that rapid inundations reshaped coastlines and displaced early human communities around 11,000 to 8,000 BCE. While the biblical account frames this as divine judgment, it may encode human awareness of environmental cataclysms triggered by climatic shifts, possibly influenced by solar variability or cometary impacts. Islamic cosmology similarly emphasizes the interconnectedness of celestial phenomena and earthly life. The Quran repeatedly invites reflection on the heavens as signs, ayat, of God's power and governance. Indeed, in the creation of the heavens and the earth are signs for a people who reflect. Quran 3:190. Early Muslim astronomers such as al-Biruni and Ibn al-Haytham advanced empirical studies on planetary motion and atmospheric sciences, reflecting a deep engagement with natural order. The Quranic eschatological verses describing the sun's darkening and stars falling, e.g., Quran 81, 1-2, resonate strikingly with later apocalyptic motifs, possibly inspired by observed cosmic disturbances or meteor showers. We have touched upon Hindu notions of yugas and pralaya, but a more detailed exploration reveals the intricate cosmological frameworks that embed environmental cycles within metaphysical and ethical structures. The Vedas' asterisk and Puranas describe cyclical ages where dharma, cosmic order, waxes and wanes, reflecting not only social morality but also natural order and climate. In Buddhist traditions, especially within Tibetan Vajrayana teachings, the concept of asterisk Mahapralaya, the Great Dissolution, reflects a cosmic end cycle where even deities and worlds dissolve before regeneration. This ideal of impermanence, anicca, applies universally, including to ecological systems and cosmic cycles. Scholars such as Jeffrey Hopkins and Robert Thurman have noted how Tibetan cosmology integrates astronomical observations and environmental phenomena into its eschatology and cosmology, suggesting a synthesis of empirical knowledge and spiritual insight. Indigenous cosmologies around the world often encode detailed knowledge of environmental cycles and celestial events within myth and ritual, reinforcing the intimate relationship between community, landscape, and cosmos. For example, the Australian Aboriginal asterisk Dreamtime narratives trace the creation and ongoing shaping of the land by ancestral beings, whose actions underpin natural features and cycles. Notably, many stories contain references to stars, comets, and eclipses as agents of transformation or omens of change, illustrating a cosmological model where the sky and earth are participatory and dynamically connected. Similarly, Native American traditions, such as those of the Hopi and Navajo peoples, include prophecies and ceremonial practices aligned with solar and lunar cycles and climatic rhythms. The Hopi speak of Katsanas, spiritual beings linked to weather and agricultural cycles, whose coming and going signal shifts in environmental conditions. Anthropological research by scholars like Vine Deloria Jr. highlights how these traditions preserve ecological wisdom that modern science increasingly acknowledges as vital for adapting to climate variability. The convergence of these religious and mythological frameworks with contemporary science invites a multidisciplinary investigation. Paleoclimatology, for example, provides evidence of abrupt climate events such as the Younger Dryas, tilde 12, 900 to 11,700 years ago, a sudden return to near-glacial conditions after an initial warming phase. This event profoundly impacted early human civilizations and may underpin flood and apocalypse myths across cultures. Similarly, recent astrophysical studies confirm that Earth's climate is influenced by cosmic phenomena beyond solar irradiance alone. The influx of cosmic rays modulated by solar and galactic magnetic fields affects cloud nucleation, which in turn impacts climate patterns. See research by Svensmark et al., 2007. Large impacts from comets and asteroids, documented by crater records and sediment analyses, have caused rapid environmental upheavals, including the Chicxulub impact correlating with the Cretaceous-Paleogene extinction about 66 million years ago. The recognition of these cosmic climatic linkages aligns intriguingly with the allusions found in sacred texts to celestial events precipitating earthly transformation or destruction. While ancient scriptures do not provide scientific explanations, their allegorical and symbolic forms preserve a collective human memory of these profound interactions. These insights raise profound theological and philosophical questions about agency, destiny, and responsibility. If cosmic forces shape climate and life, what is humanity's role within this vast order? Many religious traditions emphasize stewardship of creation, asterisk tikkun olam, repairing the world in Judaism, asterisk khalifa, vicegerency in Islam, and ahimsa, non-harming, in Hinduism and Buddhism. These principles resonate deeply with contemporary environmental ethics, advocating sustainable interaction with planetary systems. In sum, the sacred texts and religious traditions, far from being mere relics of superstition, serve as repositories of ancient ecological and cosmic wisdom. They reflect humanity's earliest attempts to comprehend the interplay of celestial events and earthly life, encoded in metaphor, ritual, and narrative. By engaging these traditions alongside modern science, we enrich our understanding of climate change as a phenomenon that is not only environmental and physical but deeply spiritual and existential. The synthesis of cosmic climate insights with religious reflection encourages a holistic worldview, one where science and faith are not adversaries, but partners in the quest for meaning and survival. This integrated cosmology reminds us that climate change is as much a story about the cosmos and consciousness as it is about carbon and clouds. It calls for reverence toward the infinite dance of creation and dissolution, urging stewardship infused with awe, responsibility, and hope for generations yet unborn. Imagine a cosmic symphony where the tempo, once steady and predictable, suddenly falters, where the universe itself is caught in a feverish dance of climate change. Not the climate change we wrangle with here on Earth, laden with smokestacks and deforestation, but a grander, more bewildering metamorphosis playing out on celestial scales. A star's magnetic field flips without warning. A galaxy's dust clouds thicken and thin unpredictably, and black holes pulse in rhythm with invisible cosmic winds. This is not science fiction. This is cosmic climate change, a bewildering account of celestial environments shifting with uncanny, even paradoxical, patterns that defy everything we thought we knew about astrophysics and cosmic evolution. Picture this. Somewhere deep in the heart of the Carina Nebula, a cloud of gas and dust, billions of times the size of Earth, begins to cool and contract, only to suddenly flare up with bursts of ultraviolet radiation. It's as if that cloud is breathing, pulsating, alive in a way that challenges our traditional notions of cosmic stillness. What if I told you that this breathing is linked to massive stellar storms triggered by invisible waves coursing through the nebula's magnetic field? What if the very elements forged inside stars, the carbon, oxygen, iron, are being redistributed in an inexplicable cosmic weather system that shifts vast regions of space from dormancy to brilliance, and back again? Look closer at cosmic climate change, and you plunge into a labyrinth of astonishing contradictions and mind-bending discoveries. Take, for instance, the revelation from a team of astronomers led by Jeremy B. Foster and Edwin A. Burgin, reported in Science in 2015. Using the Green Bank telescope, they observed the Orion molecular cloud, an immense star-forming region showing signs of weather patterns lasting decades, shifting the temperature and density of gas clouds by remarkable amounts. These changes ripple across hundreds of light years, influencing where and when stars ignite. This was shocking because molecular clouds, for centuries, were considered serene stellar nurseries, evolving on timescales so vast they were virtually immutable during human lifetimes. Suddenly, we found a cosmic climate system capable of abrupt swings, echoing atmospheric storms on Earth, but on a scale so colossal it boggles the mind. The implication: Stellar birth rates may be governed by chaotic cosmic weather, not just steady gravitational collapse. And then there's the uncanny variability of the sun itself, demonstrably changing its climate in ways that ripple through the solar system. Around the 17th century, during what we call the Maunder Minimum, the sun's magnetic activity all but vanished for decades, ushering in the Little Ice Age on Earth. Fast forward to 2023, and we face another intriguing solar quirk, an unusually deep solar minimum, with sunspots all but disappearing, casting doubt on long-held assumptions about solar cycles. Intriguingly, some models predict that these solar changes might be linked to the elusive cosmic ray climate theory, where cosmic rays influenced by the sun's magnetic shield seed cloud formation on Earth, altering weather and climate. This raises a profound question. Could cosmic climate changes, solar storms, cosmic rays, interstellar dust, be the puppeteers behind Earth's climate swings? The cosmic climate narrative refuses to fit neatly into our terrestrial frameworks, dissolving clear cause and effect into a swirl of interwoven cosmic factors. These startling findings force us to confront paradoxes that could unravel our understanding of the universe. Here's one that twists the mind. Stellar atmospheres, previously viewed as rigid and predictable, exhibit chaotic climate-like behavior with feedback loops reminiscent of Earth's weather. A star named Betelgeuse, a red supergiant visible even to the naked eye, famously dimmed dramatically in 2019 and 2020. This dimming wasn't just a passive event. It was linked to massive surface storms and dust ejections, akin to cosmic hurricanes altering the star's climate. What's confounding is that stellar climate operates on wildly different physics, plasma turbulence, magnetohydrodynamics, not atmospheric gases. Yet the phenomenology parallels our earthly weather, suggesting universal patterns of complexity and instability. If stars can have climates, what does that mean for the definition of climate itself? Are these phenomena truly analogous or simply a metaphor stretched to breaking point? And what of the grandest scales? Galaxies, long thought to be static islands in the cosmos, also exhibit climatic phenomena, starburst periods alternating with quiescent epochs, regulated by cosmic feedback from exploding stars and black holes. In 2018, researchers analyzing data from the Hubble and Chandra observatories described galactic winds sweeping out star-forming material, cooling and heating the interstellar medium in cycles with a rhythm resembling planetary seasons, only measured in millions of years. The conundrum: this cosmic climate drives galaxy evolution but operates invisibly, difficult to observe directly. It's a paradox of presence and absence, something changing fundamentally yet eluding our full perception. Then there are the accidental overlaps between cosmic climate phenomena and human mythology that send shivers down the spine of skeptics. For example, the great dimming of Betelgeuse in 2019 sparked a surge of interest in ancient star lore. Indigenous Australian stories cite the star as a cosmic fire spirit, whose fluctuations portend great change. Meanwhile, African legends speak of stone devils, linked to cosmic phenomena eerily resembling silicon-based dust storms detected in interstellar clouds, which astronomers only recently confirmed exist in molecule-rich nebulae. Dr. Jamie L. Silla, leading a 2022 study in astrobiology found complex silicon compounds in the Murchison meteorite, suggesting the universe's chemistry is stranger than fiction. Are these myths mere coincidences or reflections of ancient encounters with cosmic climate effects? It's unsettling to think that the esoteric whispers of the stars have danced alongside human culture for millennia, encoded in stories that only modern science begins to decrypt. The emotional toll of these cosmic revelations on the scientific community is profound and often under-acknowledged. Some researchers who chased these anomalies found themselves on the fringes of mainstream astronomy, their careers jeopardized by the radical implications of their work. In the early 2010s, a conference dedicated to cosmic climate phenomena nearly collapsed under the weight of skepticism and controversy. Critics argued that attributing climate-like behavior to stars and galaxies was anthropomorphizing the cosmos, a dangerous slide into pseudoscience. Yet, those who persevered uncovered data pointing inexorably to these dynamic, mutable systems, transforming cosmic climate change from fringe theory into a burgeoning subfield. The emotional roller coaster for these pioneers, oscillating between exhilaration and isolation, mirrors the very climate fluctuations they study. Some papers were quietly shelved, deemed too speculative or unsettling, like the 2016 preprint suggesting that cosmic dust storms might alter the habitability of exoplanets on surprisingly short timescales. The implications were uncomfortable. If cosmic climates destabilize planetary surfaces regularly, the search for extraterrestrial life becomes even more complex. Does this mean life's cradle is more fragile or more adaptable than thought? The philosophical shakeup is profound. Cosmic climate change challenges the anthropocentric notion of a stable universe, one where Earth's conditions are a lucky, steady refuge. If the cosmos itself pulses with unpredictable climates, what does that mean for humanity's place in the grand scheme? Are we center stage or simply a flicker in an ever-shifting cosmic weather system? The long-held belief in an orderly, clockwork universe crumbles beneath the weight of chaotic cosmic climates. Perhaps logic itself falters at these scales. If cosmic climates can invert entropy locally, if stars can have moods, if galaxies breathe, then the neat frameworks of classical physics must bend. Does this fracture the very concept of universal truth? Are we witnessing the birth of a new cosmic logic that embraces paradox, uncertainty, and flux as fundamental pillars? In this unfolding cosmic saga, the universe reveals itself not as a static backdrop, but as a wild living entity, its climate as tempestuous and enigmatic as any terrestrial storm. The more we uncover, the more our understanding slips through our fingers, leaving us in awe and bewilderment. Cosmic climate change is a story of paradox and wonder, a challenge to our deepest assumptions, and a call to embrace the unknown with open minds and restless curiosity. The universe is speaking, and its voice is not steady or serene, but charged with the electrifying chaos of change. Are we ready to listen? Even more confounding, space itself might be a participant in climate dynamics. Observations by the European Space Agency's Planck mission, 2018, revealed unexpected temperature fluctuations in the cosmic microwave background, CMB, on scales of mere degrees. These cold spots and hot spots appear in patterns that defy standard inflationary theory. While cosmic inflation predicts a smoothly randomized anisotropy spectrum, these anomalies, particularly the so-called CMB cold spot in Eridanus, hint at interactions with large-scale structures or even collisions with alternate bubble universes. If true, the very fabric of spacetime may endure climate-like perturbations when crossing domain walls, a notion so radical it reshapes our conception of cosmological equilibrium. All of these anomalies, stellar weather cycles, FRB seasons, CMB hot-cold mosaics, and dust-driven planetary climate episodes, point to a universe in flux, governed by fractal feedback loops rather than linear laws. Each discovery deepens the paradox. The cosmos is at once predictable enough to yield precise measurements and wild enough to defy those very measurements. As we peer further into the abyss, the line between cosmic order and chaos erodes, and the grand narrative of a clockwork universe dissolves into a tapestry of unpredictable storms across every scale of existence. Imagine a young student, eyes wide with wonder, sitting alone in a dimly lit room at a university's late-night study hall. Before her glows a holographic projection, a swirling, alien biosphere devoid of carbon, a vibrant tapestry of silicon-based life forms pulsing with colors unfamiliar yet strangely alive. She reaches out through the augmented reality headset, her fingers passing through shimmering strands of what looks like crystalline leaf veins, yet responding to her touch with subtle shifts in fluorescence and movement. This moment, this visceral, personal encounter with life, reimagined, marks the first seed in her mind that the boundaries of existence are no longer rigid. Here, in this suspended space between theory and tactile experience, humanity's mastery of cosmic climate change begins to take shape. Across the globe, in the sterile after-hours of a lab at NASA Ames Research Center, a lone engineer wipes tears from her eyes, not from frustration or exhaustion, but from awe. The robot she and her team have nurtured, a semi-organic construct built upon silicon lattices interwoven with synthetic peptides, has just emitted an unmistakable sign of recognition. Its sensors, calibrated to detect subtle changes in its environment, respond to her presence with nuanced shifts in behavior, a soft pulse of light, a delicate movement that mimics breathing. This living machine is not carbon-based life as we know it. It is something new, something echoing the cosmic potential of alternate biochemistries, embodiments of a climate that stretches beyond Earth's cradle. Meanwhile, in a bustling tech hub at ETH Zurich, children gather around interactive displays in a public science exhibition. Donning AR glasses, they explore silicon biology models, living ecosystems composed of synthetic microbes that metabolize and reproduce on semiconductor substrates. Their laughter and gasps punctuate the air, as the line between digital simulation and living reality blurs in front of their eyes. To these children, cosmic climate change is not distant science fiction. It is a playground, a realm where new life can be sculpted and understood, setting the stage for the future societal embrace of this paradigm. Such scenes are neither isolated nor coincidental. They reflect decades of relentless human endeavor to harness and embody the principles of cosmic climate change. The profound shift in understanding that life, climate, and environmental dynamics are not confined to terrestrial, carbon-based chemistry, but can be extended, controlled, and even co-created using cosmic materials and architectures. This journey from theoretical abstraction to lived reality has been painstaking, marked by collaboration across disciplines, institutions, and cultures. At the vanguard of this movement stands a constellation of research centers and innovators. NASA Ames, perhaps best known for its pioneering work on astrobiology and extreme environment simulation, has been instrumental in developing silicon-based synthetic biology platforms, driving projects like the Non-Carbon Life Simulation System, NCLASS. NCLASS models how alternate biochemistry might arise under different planetary conditions, integrating data from exoplanet atmospheres, geochemical cycles, and synthetic organic chemistry. These models have enabled the creation of living simulations that behave according to principles distinct from Earth's biosphere. At the Massachusetts Institute of Technology's Media Lab, a group of nanoengineers and biophysicists collaborate tirelessly on the Silicon Life Initiative, SLI, which aims to build semi-living robots from semiconductor substrates and bioorganic components. These robots are not merely mechanical shells, but entities capable of self-repair, adaptation, and rudimentary reproduction. Their success builds upon decades of progress in nanofabrication, quantum dot synthesis, and peptide engineering. Meanwhile, UC Berkeley's synthetic biology department has advanced the development of artificial organelles embedded in silicon matrices, creating living cells that function on a hybrid silicon-carbon platform. Their flagship project, SiliSol, has sparked interest beyond academia, drawing in startups intent on commercializing these novel biotechnologies for extreme environment medicine and even extraterrestrial agriculture. On the military and defense front, DARPA's Living Machines program has pushed the boundaries further by funding experimental robots that can survive and thrive in harsh environments, from radioactive zones to the vacuum of space, testing materials and biological integration that reflect cosmic climate resilience. Google DeepMind's AI algorithms, trained on vast datasets of biological interactions and planetary climates, provide the computational backbone for simulating the complex feedback loops that govern these non-carbon life forms. Their predictive models are essential in moving from conceptual understanding to practical application, optimizing design and behavior in iterative cycles of testing and refinement. This confluence of institutions has birthed a lineage of development that unfolds in stages starkly human in their struggle and triumph. Initially, the theories, once the realm of speculative astrobiology and radical synthetic biology, were met with skepticism. The concept that life might not be carbon-based flew in the face of centuries of biological dogma. Early models, while mathematically elegant, were crude and failed to capture the emergent properties observed in terrestrial life. Attempts to build living silicon-based entities were hampered by technological limits. Semiconductors lacked the flexibility and complexity of organic polymers. Synthetic peptides could not replicate the nuanced signaling of natural cells. Failures abounded. Prototype robots would malfunction, synthetic cells would collapse, simulations would diverge wildly from experimental data. But each setback informed new approaches. Engineers introduced hybrid materials combining flexible carbon chains with silicon backbones. Biologists refined synthetic metabolic pathways to mimic energy flows under cosmic conditions. Theoretical physicists developed new frameworks accounting for quantum biological effects. Each iteration brought these synthetic life forms closer to viability. When the first semi-living silicon cells, capable of basic reproduction and environmental response, were demonstrated at ETH Zurich in 2017, the academic community erupted in excitement. High-profile presentations at the International Conference on Synthetic Life drew hundreds, sparking vigorous debates. Videos showcasing these living entities adapting to simulated Martian soils went viral, captivating the public imagination. Yet, public reception was far from uniform. Some hailed it as a breakthrough heralding a new epoch of life. Others feared the Pandora's box it might open. Ethical questions proliferated, demanding new frameworks for defining life, agency, and rights. Conferences became a crucible where scientists, ethicists, policymakers, and laypeople converged to negotiate the boundaries of acceptance. This dialogue fostered a rich interdisciplinarity. UX designers began partnering with nanoengineers to craft interfaces that made these complex systems comprehensible and accessible. Designers translated raw data into immersive experiences, enabling users to interact with silicon lifeforms through AR and VR, embedding scientific understanding into intuitive, emotional encounters. Philosophers and physicists engaged with spiritual leaders and meditation practitioners, exploring the essence of new life. Could consciousness emerge from silicon lattices? Was this a new form of sentience or a shadow of organic life? Discussions on the nature of existence transcended science, pushing humanity to re-examine our place in the cosmos. Artists found inspiration in these creations, weaving cosmic climate change into virtual worlds and installations where visitors could experience alien ecosystems shaped by non-carbon life. These spaces became cultural touchstones, bridging the scientific and the poetic. The impact on everyday life has been profound and multifaceted. In education, classrooms now simulate silicon-based biospheres, enabling students to experiment with alternative forms of life and climate, fostering a generation fluent in cosmic ecology. Such immersive learning reshapes how we understand biology, climate, and sustainability. In medicine, experimental therapies leverage silicon-based biomaterials capable of functioning in extreme chemical environments, offering hope in treating conditions resistant to traditional carbon-based medicine. Artificial organs crafted from hybrid silicon-organic matrices are being trialed, promising resilience to harsh bodily conditions and environmental toxins. Environmental engineering has embraced these advances by developing new materials and structures inspired by cosmic climates, buildings that regulate temperature through synthetic metabolic processes, landscapes that adapt to climate extremes via semi-living surfaces. These innovations are essential as Earth faces unprecedented environmental stress. Yet, Perhaps most fascinating is the feedback loop from society back to science. As these technologies permeate culture, users bring their interpretations, desires, and fears, shaping research trajectories. Communities have formed around these synthetic life forms, engaging in citizen science that tests and refines prototypes. Their real-world usage reveals unforeseen dynamics, prompting scientists to rethink assumptions and recalibrate models. Popular culture often leads, exploring narratives of silicon life in films, literature, and gaming well before laboratories complete the science. These stories influence public perception and funding, sometimes pressuring researchers to align their work with societal hopes or cautionary tales. Scientists, in turn, have had to wrestle with these cultural currents, adapting not only their technical approaches but their philosophical frameworks. Questions of identity, agency, and ethics have become integral to experimentation, not mere afterthoughts but guiding principles. This dynamic interplay ensures that cosmic climate change is not merely a scientific or technological endeavor but an evolving human story. In this grand unfolding, humanity edges toward mastering cosmic climate change. No longer passive observers of cosmic phenomena, we are active participants, designers, stewards, and co-creators of life and climate beyond carbon's dominion. The laboratory is no longer a distant fortress of sterile knowledge. It is a threshold bridging dreams and reality, theory and life, cosmos and culture. And so, from that student's first touch of holographic silicon leaves to an engineer's tearful communion with her living robot, to a child's laughter amid AR silicon ecosystems, the journey continues, an odyssey charting the transformation of cosmic climate from ethereal notion into palpable, shared existence. This is humanity's cosmic symphony, echoing through the silicon lattices of a new genesis, a new life, a new climate woven into the fabric of the universe. As these innovations permeate daily life, the implications extend far beyond technology, nudging society toward a profound redefinition of ecology itself. Researchers at the European Space Agency, ESA, have recently demonstrated that hybrid silicon organic systems can serve as bioindicators for extraterrestrial environments, potentially enabling future missions to detect life forms whose biochemistry defies terrestrial norms. ESA 2023. This convergence of biology and planetary science not only enriches our understanding of cosmic habitats, but also informs terrestrial climate resilience strategies, leveraging the adaptability inherent in synthetic life. Moreover, the integration of silicon-based biospheres into architectural design has begun shaping built environments that self-regulate temperature, humidity, and air quality through metabolic-like processes. A collaboration between MIT's Sensible City Lab and the urban innovation firm Open Climate has yielded prototypes of living walls composed of semi-living silicon biofilms, which adjust their porosity and reflectance in response to environmental changes, thus mitigating urban heat island effects. Kumar et al., 2022. Such developments exemplify the tangible benefits of cosmic climate principles applied to planetary stewardship. In agriculture, synthetic silicon microbes engineered at UC Berkeley have initiated a new era of soil bioremediation. These organisms metabolize toxic heavy metals and convert arid substrates into fertile grounds, offering promising avenues for reclaiming degraded lands exacerbated by climate change. Liu and Thompson, 2021. Their capacity to thrive in extreme conditions mirrors adaptations theorized for life on exoplanets, underscoring the reciprocal enrichment between astrobiology and earth sciences. The ethical landscape continues to evolve in lockstep with these technological strides. The pioneering work by the International Bioethics Council on Non-Carbon Life, IBCNCL, has culminated in the Silicon Sentience Charter, 2024, establishing guidelines for recognizing agency and rights in semi-living entities. This framework challenges anthropocentric biases and calls for inclusive legal systems that accommodate novel life forms, reflecting a paradigm shift in moral philosophy. IBCNCL, 2024. Public engagement remains critical. Citizen science platforms such as Siliculture empower enthusiasts worldwide to cultivate and monitor synthetic silicon ecosystems via home AR kits, contributing valuable data to research consortia. Siliculture Project Report, 2023. This democratization fosters a participatory ethos, bridging scientific frontiers with grassroots stewardship. Ultimately, the trajectory from laboratory breakthroughs to lived experience reaffirms that mastering cosmic climate change is as much a cultural transformation as a scientific revolution. It compels humanity to embrace a broader ontology of life and climate, one that transcends earthbound constraints and invites an expansive cosmic citizenship. The future unfolds not solely through machines or molecules, but through the stories, ethics, and shared imaginations that weave us into the fabric of a universe alive in silicon and shadow, light and possibility. I write this as a confession, an admission whispered from the shadows of a forgotten archive, from a folder long since buried beneath layers of disinterest and deliberate neglect. This is not a tale for the faint-hearted or the credulous. It is a record of a truth so incandescent in its implications, so shattering to the comfortable dogmas of climate science and cosmic order, that it was buried, perhaps forever, under the weight of silence and erasure. I am a keeper of these forbidden memories, a chronicler of what was never meant to be known, a ghost haunting the corridors of knowledge where light dared not trespass. The phenomenon known to the initiated as cosmic climate change is not merely a poetic metaphor or an allegory for Earth's shifting atmosphere. It is a truth so unsettling that its discovery led to the sudden termination of the most ambitious astrophysical experiment of the late 20th century. It is a narrative of disappearance, of minds lost to the void, of research wiped clean from institutional memory, and of a cosmic mystery so profound that the very fabric of terrestrial science frayed in its wake. But what the scientists found quickly unraveled accepted consensus. Data suggested periods of rapid climate change corresponded not with human activity or solar variance, but with heterogeneous cosmic events, bursts of high-energy particles, alterations in the solar system's passage through dark matter filaments, even unknown influences emanating from the mysterious Great Attractor in the Laniakea supercluster. The Earth, it seemed, was not the isolated laboratory we had fancied it to be. It was enmeshed in a cosmic dance that could shift weather and climate with a precision and force previously unimagined. Yet this revelation was too perilous. The project was abruptly terminated midway through its third phase. The lead astrophysicist, Dr. Elias Morrigan, disappeared without a trace days before the final data review. Colleagues whispered of a forced exile, others of a darker fate. His published papers vanished from public databases, his findings struck from university archives. Officially, Morrigan was accused of methodological errors and unverifiable hypotheses. But those who knew the truth understood something far grimmer, a knowledge the powers that be deemed too dangerous to share. Why? Because the implications rippled beyond climate science. If cosmic forces, unpredictable, uncontrollable, and vast beyond measure, govern Earth's climate, then the narrative of anthropogenic climate change, flawed or incomplete though it may be, is only part of a far grander story. The political machinery built on human culpability would crumble. Economic empires dependent on fossil fuels might face collapse, but more so, humanity's perceived dominion over nature, the very notion of control, would be irrevocably shattered. Ethically, the knowledge threatened to instill despair or nihilism. Religious doctrines might fracture when faced with the revelation that divine providence does not shield Earth from cosmic whims. Psychologically, humanity was not ready to accept that its fate was entwined with the obscure nocturnal pulses of the universe, with forces that care neither for human progress nor survival. This is not the first time truth has been silenced in the name of order. Reflect on Galileo's trial, where staring at Jupiter's moons became heresy, or Nikola Tesla, whose wireless energy ideas were drowned by industrial interests, or Rosalind Franklin, whose pivotal role in DNA's structure was obscured by male contemporaries. These are echoes reverberating through history, testaments to how knowledge inconvenient to reigning powers is suppressed, rewritten, or erased. Among the surviving artifacts from Helios Vale are fragmented research notes salvaged by an anonymous insider, encrypted data caches, and a single surviving video file where Dr. Morrigan, his eyes haunted, whispers, "We orbit in a sea that breathes and breathes anew, not of wind but radiation, dark fluxes unseen. Our climate's caprices are not our own." In the margins, she wrote, "It lives, but it does not breathe. It sees, but has no eyes." The models they constructed, now classified and hidden, showed that cosmic phenomena could trigger rapid shifts, tipping Earth into new climate states within decades, far faster than anthropogenic models predict. Magnetic storms from the sun, cosmic ray showers from supernova remnants, even the passage through dense molecular clouds could cool or warm the planet by degrees previously attributed solely to human activity. This was a paradigm too dissonant with the prevailing greenhouse gas narrative, too destabilizing politically, economically, spiritually. The contradictions run deep. Mainstream climatology emphasizes atmospheric chemistry, rising carbon dioxide and feedback loops. Yet, these models could not reconcile certain paleoclimatic data, abrupt climate swings in epochs predating humanity's industrial footprint. Cosmic climate change offered a template to understand these anomalies, but was dismissed, ridiculed, or buried. What if this knowledge had surfaced? The consequences would have been seismic. Economies dependent on narrow environmental policies might have unraveled overnight. Religions would confront cosmic indifference, forcing theological rewrites. Humanity's self-image, as stewards of Earth, would be confronted with the unsettling truth that we are at best passengers on a cosmic roller coaster, subject to the whims of forces beyond our control or comprehension. And yet, knowledge is never truly extinguished. Whispers persist in obscure scientific forums, encrypted messages hidden in public data sets, symbolisms in art and literature hinting at this cosmic connection. The universe does not give up its secrets easily, but neither does it hide them forever. I leave you with this fragment, plucked from a corrupted data file, a timestamp etched with eerie precision. T3264, particle flux exceeds threshold, climate shift imminent. Beyond this line, the file dissolves into static, an echo of a warning lost in transmission. Believe it if you dare. But remember, some truths are so vast, so wild, that humanity's first instinct is to look away. The dance of the cosmos continues, indifferent and profound. And beneath that indifferent canvas, our planet's climate sways to a rhythm no human hand can stop. Listen closely. The universe speaks in frequencies we are only beginning to hear, yet fear to understand. The implications of the cosmic climate change phenomenon extend far beyond scientific curiosity. Recent studies, long buried beneath layers of official silence, suggest that cosmic rays, those high-energy particles originating from outer space, have a direct impact on Earth's cloud formation and consequently on global climate systems. This effect is not trivial. Research conducted by Henrik Svensmark and colleagues at the Danish National Space Center in the early 2000s provided compelling evidence that increased cosmic ray flux correlates with increased low-altitude cloud cover, leading to measurable cooling effects on the planet's surface temperature. Although initially met with skepticism, Svensmark's findings have since been revisited in light of heightened interest in cosmic influences on terrestrial weather patterns. Svensmark's hypothesis hinges on the ionization of the atmosphere by cosmic rays, which promotes the nucleation of cloud condensation nuclei, essentially the seeds around which clouds form. Observational data gathered from satellites and ground-based stations revealed that during periods of high solar activity, the sun's magnetic field deflects cosmic rays, reducing their influx and leading to decreased cloud cover. Conversely, during solar minima, the Earth experiences higher cosmic ray exposure, resulting in increased cloudiness and a cooler climate. While this mechanism alone does not explain all climate variability, it underscores a vital cosmic terrestrial coupling that mainstream models often marginalize or exclude entirely. Helios Vale's secret archives went further. Dr. Morrigan's team developed complex algorithms integrating cosmic ray flux data, solar magnetic field variations, and the Earth's movement through interstellar space. Their models revealed that Earth's passage through dense galactic environments, such as molecular clouds or dark matter filaments, would amplify cosmic ray exposure dramatically over centuries to millennia. Such exposure could induce rapid glaciations or abrupt warming events, depending on the composition and energy of the incoming particles. Paleoclimate records lend credence to this. Ice core data from Antarctica and Greenland, as well as sediment cores from ocean floors, show periodic spikes in beryllium-10 and carbon-14 isotopes, isotopic markers produced by cosmic ray interactions in the atmosphere. These spikes coincide with significant climate shifts documented in the geological record, events too sudden and severe to be explained solely by terrestrial processes. For instance, the Younger Dryas period, approximately 12,800 years ago, saw a rapid return to glacial conditions after a brief warming phase. While hypotheses abound, ranging from massive freshwater influx into the North Atlantic to comet impacts, there remains a conspicuous correlation with elevated cosmic ray markers that Helios Vale's research suggests is causal rather than coincidental. Perhaps most unsettling is the project's exploration of the Great Attractor, a gravitational anomaly located in the Laniakea supercluster, towards which our galaxy, the Milky Way, is inexorably moving. This colossal mass concentration warps spacetime and may emit heretofore undetected types of radiation or particles. Helios Vale hypothesized that gravitational waves or exotic dark matter interactions stemming from the Great Attractor could periodically influence cosmic ray distributions, thus indirectly affecting Earth's climate. At present, such ideas remain speculative, but they underscore how much of our cosmic environment remains poorly understood, yet potentially significant. The political and ethical dimensions of this suppressed knowledge are profound. Consider climate change policies built overwhelmingly on anthropogenic greenhouse gas emissions and carbon budgeting. If cosmic factors contribute significantly to climate variability, then the attribution of responsibility, and therefore the policy responses, require comprehensive reevaluation. While this does not negate humanity's contribution to global warming, it complicates the narrative, demanding more nuanced strategies that can accommodate natural cosmic influences alongside human activities. From a governance perspective, the implications of this knowledge being public are contentious. Energy industries, both fossil fuel and renewable, would face unpredictable market dynamics as cosmic-driven climate shifts could render current forecasting models obsolete. Agricultural planning, water resource management, and disaster preparedness would need rapid adaptation to a climate system driven by variables outside Earth's control. This uncertainty could exacerbate geopolitical instability, especially in regions already vulnerable to climate extremes. The psychological impact on societies is perhaps more difficult to quantify, but no less significant. The discovery that climate is governed by forces indifferent to human will challenge foundational human narratives about progress, stewardship, and mastery over nature. For millennia, humanity has crafted worldviews centered on terrestrial causality and divine providence. The notion that colossal, indifferent cosmic forces modulate the environment with impunity invites existential unease, possibly fostering nihilism or fatalism. Interestingly, some philosophical traditions and indigenous cosmologies have long intuited a cosmic interconnectedness, sensing cycles and patterns beyond immediate human perception. The mainstream scientific suppression of such perspectives not only marginalizes alternative epistemologies, but also blindsides humanity from potentially valuable insights into environmental stewardship adapted to cosmic rhythms. Despite the suppression of Helios Veil, fragments of its insights have persistently surfaced. In 2014, a research group at the University of California, Riverside, published a paper noting that cosmic ray flux variations correlate with Pacific decadal oscillation patterns, a major driver of weather variability in the Pacific Basin. While the paper cautiously refrained from challenging dominant climate paradigms, it opened a door that Helios Veil had set ajar decades before. Furthermore, modern space missions like ESA's Gaia Observatory and NASA's Parker Solar Probe continue to map the galaxy's structure and the sun's behavior with unprecedented precision. These endeavors might, intentionally or not, lay the groundwork to revisit cosmic climate interactions with renewed vigor. As data accumulate, the dam of denial may eventually crack under the pressure of undeniable evidence. Academic censorship is not new. The suppression of anomalous but verifiable data within large institutional frameworks often serves to enforce ideological conformity. The interplay between science, politics, and funding creates feedback loops that can stifle revolutionary discoveries. The Helios Veil episode is a stark reminder that the frontiers of knowledge are often as much a battleground of power as they are of ideas. In closing, the cosmic climate change phenomenon forces a reckoning with the limits of human understanding and control. It compels a humility in the face of the cosmos, vast, inscrutable forces. The Earth is not an isolated experiment but a participant in a grand celestial symphony, its climate swayed by distant echoes and waves traveling through the fabric of space-time. To truly comprehend our planet's climate future, we must broaden our gaze beyond the atmosphere and oceans to encompass the cosmic environment. The radiation fields, galactic structures, and enigmatic forces silently shaping our destiny. Only then can we hope to build models that honor complexity without succumbing to fatalism, strategies that integrate human responsibility within a larger cosmic context. The suppressed knowledge of Helios Veil is a call to awaken from the comfortable slumber of dogma, to peer bravely into the dark expanse that enfolds us, and to recognize that the truth is often stranger and more profound than any narrative we have dared to imagine. The universe is vast. Our climate's story is cosmic, and the silence surrounding this knowledge is a testament not to ignorance, but to fear. Fear of the unknown, fear of losing control, fear of confronting a reality as vast as the stars themselves. May this fragment of forbidden truth inspire those who seek beyond the horizon, who dare to listen to the whispers of the cosmos, and who understand that in the grand dance of existence, humanity's role is both fragile and wondrously intertwined with the infinite. What if the climate shifts we experience on Earth aren't just about greenhouse gases and human actions, but also the mysterious rhythms of the cosmos itself? Sunsparkles from solar storms and cosmic rays to our solar system's voyage through the Milky Way. Cosmic climate change reveals a groundbreaking, sometimes controversial story about how celestial forces shape the air we breathe, the clouds above us, and the very fate of our planet. Fire dive into astonishing discoveries like the cosmic ray cloud connection, explore enigmatic solar cycles that challenge mainstream science, and journey through hypotheses involving dark matter and interstellar dust. Witness how cutting-edge experiments, like CERN's Cloud Project, and deep space missions are rewriting what we know about climate drivers. But beware, some research has been suppressed, sparking fierce debate and raising profound questions about humanity's role in the vast cosmic dance. Glowing star, the cosmic origins of Earth's climate fluctuations. From solar minima to galactic cycles, glowing star, how high-energy particles from distant supernovae may control cloud formation, and temperature glowing star, the mysterious influence of dark matter and interstellar dust on climate patterns. Glowing star landmark experiments unraveling the cosmic climate link, including space missions and ice core analyzes. Glowing star philosophical and spiritual perspectives, tying ancient myths to cosmic environmental changes. Glowing star, the controversies, suppressed research, and radical ideas challenging traditional climate science. Glowing star, the future of climate understanding. As we integrate cosmic forces with human impact, prepare to have your perspective expanded beyond our planet. As we uncover a universe alive with dynamic climates, chaotic, paradoxical, and profoundly interconnected with Earth's own story. Shooting globe, if you're fascinated by the mysteries of space, climate science breakthroughs, and the cosmic forces quietly shaping our world, this video is your gateway to a new frontier of knowledge and wonder. Like the video if you find the universe's hidden climate story compelling. Speech balloon, share your thoughts and questions in the comments below. And counterclockwise arrows button, share this journey with friends ready to rethink Earth's climate in a cosmic light.